violet. I'm sorry?
Go ahead, Mel.
Okay. The first is a registered cover envelope from St. Louis, Missouri, April 9th, 1895, arriving at Topeka, Kansas, April 11th, 1895. Both have the word registered in capital on the front and the reverse. Now, the postal laws and regulations of 1879 issued by the post office in Washington required that registered mail, Section 822 of the regulations, required registered mail have the word registered on the origin post office appearing on the cover front. It was arbitrary on the reverse to have the word registered. Many post offices use the same hand stamp to designate registered mail, whether it be origin or arrival. The second cover is from Freedom, New York to Rochester. And here you have an example of a small post office, probably a general store, where the postmaster ran the general store and did not adhere to the postal regulations that were in force at the time. And you see at the top near the Columbian 8-cent stamp, registered number 7 appears as the only indication that this is registered. Now, both covers have stamp or entire canceled with black printer's ink as required by Section 335. The larger post offices opted for a registered in an oval, double ring oval cancellation, which normally gave St. Louis, Missouri, in this case, registered. And depending upon the post office, obviously might say San Francisco registered, etc. In black printer's ink. Black printer's ink was used at the Freedom, New York post office also. The circular date stamp was discouraged by the postal regulations for use as a canceling device because in many instances it could be very light. Okay, moving on. Let's see if we can review what the instrument we're going to be using will really be doing. There are two types. If we take a source of single wavelength light, such as a laser, and have an incident on a element or a molecular compound, there are two types of scattering that occur. One is elastic scattering, and the majority of light will be elastically scattered. Now, what's involved in that? Well, photon energy, incident photon energy at the surface of the molecular compound will be reflected at the same energy level leaving. This is an example of elastic Rayleigh scattering. There is no change in wavelength. The incident and reflected wavelength will be the same. However, a small portion of light, how small? Perhaps 1 photon in a million, that's how small, will be reflected at a different wavelength, in this case, a greater wavelength and a different color. Now, C.V. Raman received a Nobel Prize in 1930 for his work on inelastic. This is an example of inelastic light scattering. He used arc lamps. Okay, there were no lasers, obviously, in the 1920s. What's really going on here is that with Raman, the photon energy leaving is not the same as the photon energy entering or hitting the object. It is lower. The difference in energy levels are absorbed by the molecular bonds. This bond absorption will cause bond bending and vibration of the bond structure. And it is the collection of these photons by the instrument that allows us to display the shift, the Raman shift per inverse centimeter on the XY axis. These peaks are energy peaks. And They are unique to the molecular compound that we are exposing the laser to. All lasers, whether it be a 457, a 532, a 785, generate the same peaks. The peaks that we see in the Raman spectrum are the same, regardless of the laser energy source that we're using. Now, the instrument that I use is a Registry in-via reflex instrument. It's a micro analytic instrument, and it is class 1. Class 1 being that the laser beam is enclosed within an enclosure. There is a handle to the left which swings closed. You cannot operate the machine. The instrument can't be operated in the open state. You have to completely enclose the object. There are 4 microscope objectives. There's a ×5, 20, 50 long working distance microscope and a 100 for magnification with gratings, which gratings are basically prisms to separate the Rayleigh photons from the Raman photons so that we can collect the Raman photons in a silicon CCC detector, and then of course it's passed on to software. Before we use the instrument, the instrument forces us to calibrate it regardless of the laser that we're using. The calibration curve for a silicon slab within the instrument is shown in figure 2. And this is for a 532 nanometer laser used at about 3.43 milliwatts of power, which represents 10% of the laser power. The peak resonance for silicon is 520 on the Raman shift per inverse centimeter scale. I make a note here that since our objects are paper, we're looking at very sparse hand stamp on paper. It's important that we not exceed 5 milliwatts of power with our lasers. The 785 laser is rated 100 watts. We're going to be using incrementally very small amounts of power. Now, I have 3 lasers, a 457, a 532, and a 785, because experience has told me that a given laser may or may not operate correctly in producing a Raman spectrum in the background of Rayleigh photons, Rayleigh fluorescence, if you will. And I may not get a spectrum at 785 or 457, but I will get a spectrum depending upon the molecular compound using the 532. All right, so here we have figure 3 is the first cover that we're going to be looking at. It's the Topeka, Kansas, registered hand stamp and violeting, dated April 11th, 1895.
The updated financials, because we discovered
there's a lot of
that there was a slide in there that had a page that showed salaries in 2023 that were not in 10 days. So
there's a lot of audio feedback from somewhere coming. Okay. Here in figure 4, we have the Topeka, Kansas hand stamp, April 11th, 1895, registered in the instrument, being illuminated by the ×50 long working distance microscope. In figure 5, we see the typical display after running, okay? And this is at our test point S, which is the S of Kansas. We can move the mouse around in the object, in the magnified 50 times object, and pick a point, any point we want to determine the Raman spectrum. To the right is the actual spectrum that we obtained, and looking at the spectrum after baseline is corrected and truncated slightly, truncated meaning that we're looking at 200 Raman shift through 2000 Raman shift, and we see the spectrum peaks that we have. Now the question is, what does it mean? Where do we go with this information? We have no prior history on this particular ink. What we have to do now is rely on research, okay? Research of published papers, usually by scientists at museums, would be a good source on using Raman on paint chips. A simple Google of Raman spectrum violet ink will produce a series of papers that we can then look at in detail to determine if we can find a match to the spectrum that we have. And sure enough, there's a paper presented by Miss Sarasato in 2019, who's a researcher at the Metropolitan Museum of Art, and has presented a number of papers on Matisse and Van Gogh paint chips. And lo and behold, if we look at curve A and our curve, our spectrum, our waveform, if you will, you'll notice that our peaks almost match, plus or minus, within plus or minus 2 Raman shift. Our laser is a 488 nanometer laser. Mine is a 532 nanometer laser. It makes no difference what the laser wavelength is. The spectrum indicates, and she does it for me, that this is crystal methyl violet. Now, crystal methyl violet is a compound that is a derivative, was developed in Europe in 1873 from crystal methyl, which was developed in 1858. And it's really today called crystal violet. Once I've determined that I'm dealing with crystal violet, the next step for me as a researcher is to go out and buy a sample amount of commercially available crystal violet dye, which I found at a number of different sources. Hucker's Corporation has a CRYVIOL, which is crystal violet in solution, and for a nominal fee, I was able to get enough to put on printer's paper and run a Raman spectrum, which appears in figure 8. Now, once I have a spectrum of a known quantity, known crystal violet sample, I can then build a library in my software and add this Raman spectrum to that library. And then moving on, I can take the Raman spectrum determined from the data from my cover, the S, and compare it directly using a match capability within the library, pulling up library matches. I've also added the actual spectrum for my 1895 cover as well. And you can see what we're matching here are peaks. We're not interested in matching the baseline. The baseline can move up and down. The degree of match will depend upon the baseline. In this case, the baseline happens to be identical to the data I obtained on both the cover and from the Hooker's sample. So they match perfectly. And there's no doubt that I'm dealing with crystal violet. And this, by the way, is a synthetic dye. It's not an ink. And this particular violet synthetic dye can be found from all post offices within the United States, in any postal history collector of any registered cover in any catalog, picking up a 1911, 1920, 1892, 1897, 1898 will find most violet dyes were used. Now, since there was no specification that came out of the Postmaster General concerning the color to use, it's very possible that some post offices, and this is certainly the case, especially in San Francisco, where other colors we use simultaneously with violet. We may have the main post office in San Francisco using violet dye, which is crystal violet, and a red dye used in a like the Ferry Point post office, a substation where a cover was sent, and hand stamped as well. So there are two hand stamps. There's the arrival at the main post office and a transit hand stamp as well in a different color. That color typically in San Francisco is red. And that red dye is more complex than the crystal violet and subject for further research. Moving on, the second cover. We're going to do the same thing with the second cover. Now, there's a comment here that I have in the paper concerning the blue cancel of Rochester, New York, April 26, 1894, and that is, could this be Prussian blue? Well, the Raman spectrum for Prussian blue is shown below the cover. It is totally different than crystal violet, completely different. With a peak at 2153, it's a cyanide ferrous compound. And as such, it has completely different chemical formula, completely different molecular bond structure, and obviously a different spectrum. Okay. Using the same approach that we did with the previous cover and illuminating with the same microscope objective, the 50 long working distance, and picking the R, a very dark point, obtain a Raman spectrum. And now, since I have added my crystal violet spectrum to my library, I also added the 1895 spectrum to the library. I can now ask for a comparative analysis, checking this spectrum that I just obtained in red against the best match, which is crystal violet and blue. And again, the peaks match. The importance here is the peaks match. The degree of match total is over 98%, but that's immaterial. We could have a match to 50%. We're interested in peak matching, not in amplitude matching, not in the y-ordinate matching. So what we've determined now is that crystal violet was used at both post offices in two different color shades. Very important. Raman is not color sensitive. It depends only on the molecular bonds. It has nothing to do with the color. Color is a misnomer. Color can be anything. We can have color shades ranging from very light violets to deep dark blues. Crystal violet itself is a chemical compound, a synthetic compound, C25H30N3Cl. It's a chlorine salt, if you will. And the molecular bond structure is shown on the next page in the paper. This from another source, good chemical source, Millipore Sigma Corporation, which is in Illinois, readily available to provide samples of many dyes, including crystal methyl violet. And here we can see in a planar XY axis, a representation of the molecular bond structure of crystal violet. There have been a host of researchers who've looked at the bonding structure and what Raman does to what the various peaks really mean. And the last reference I have in the paper, reference 7, gives a table of the different bonding between carbon, hydrogen, nitrogen, and the ionic bond chlorine to basically a benzene ring, which is made up of the carbonium ion, H3C ion, if you will, in a benzene ring of 3, sort of a pellet-shaped molecular compound. Now, chlorine, ionic compounds in general, are difficult to detect with Raman. And we don't really see a Raman indication in the table that's provided by the researchers in reference 7. This is another way of presenting the stretching, bending, and vibration that occurs and what the peaks really mean. The one point I should make here is that we all know the speed of light is equal to wavelength times frequency of a wave. If we have a wave, we also know that E equals mc squared. So obviously, E, energy of any mass, is related to wavelength squared. And we can, of course, then clearly see that the peaks we're obtaining are really energy peaks. They're the peaks being absorbed by the molecular bonds. So our conclusion is quite simple here. This was not an ink that was being used, but a synthetic dye, number one. Number two, the color is not important. It depends only on the Raman results depend only on the molecular bonds. Okay, that's the paper basically. I can take any questions that may be asked and go over anything in more detail.
Thanks, Mel. If you have a question, please submit it through Q&A, and I should be able to let you in as a speaker. All right, Paul, give me a moment here, and I will convert you to a presenter, and then we can see you.
Okay.
All right. Please ask your question, Paul.
Okay. Can you hear me?
Yes.
Oh, jolly good. The question is really, is there a background spectrum of the paper the envelope's made of? And does that vary?
Well, Raman is a very, if we take a look at what we're using, let me answer the question by saying that, okay, to get the spectrum associated with cover number one, the S point in Topeka, Kansas, I'm using 15.7 microwatts. There is no appreciable spectrum of the paper. The paper spectrum, looking at the paper by itself, I would need some 5 milliwatts to get a spectrum of the paper. It's completely a different, the amount of power being used by my instrument is so low that I'm not getting depth of penetration to the paper. I'm basically at the scattering level of the dye.
Okay.
Okay.
And this is true
Okay,
this is true for all of the samples that I've used. I don't think I used more than, in the case of the Huckus material, it was 24.92 microwatts. And by the way, 5 milliwatts or higher can easily burn a hole in paper. As a child, I'm sure you took a magnifying glass in sunlight to a piece of paper or a leaf and focused it to get the paper to emit smoke. You can easily burn a hole. This technique can be non-invasive or invasive depending upon the user, as most techniques are. And by the way, a Raman instrument that is class 1 totally enclosed is quite expensive. Most Raman instruments are not enclosed, and goggles are required lest you damage your eyes from laser reflection. So a word of caution, you can easily damage a philatelic item. And one other point I should make, for the researcher, let's see where we are. Hang on just a second. For Miss Serrato and her, you'll notice that curve C and curve D. What she's done here is she's treating silk fabric with chemicals and heat, and other researchers have used gold nanoparticles, Sears technology, surface enhanced Raman spectrometry. And the reason for that is that it's an amplification of the very weak response due to inelastic scattering. So what we're dealing with here is, for a philatelic item, we can't heat the cover. We can't chemically treat the cover. We can't use gold or silver nanoparticle solutions to try to enhance a very weak substrate on the surface of an object. We have to treat the object the way it is. That's why I have 3 lasers. Okay. There are certain red dyes which will give me a straight line response similar to curve B that you see on her data. Straight line response, useless response. The 785, the 532 give no response at all to the red dyes of San Francisco. Even the darker red dyes of San Francisco is a good example on the Registry hand stamp. 457, yes, illuminated with a lot of background noise at extremely low power levels, 3.5 microwatts. Anything greater, I get fluorescent lines. Fluorescent being overwhelmed by Rayleigh scattering. So this is not a perfect instrument or a perfect science. There's a lot of research in the use of the instrument and research and interpretation of the data that's required. One who is not willing to study the literature is going to find it very difficult to use the instrument. The instrument doesn't, there is no canned series of libraries that you can buy that are going to result in your ability to look at the real world. You can look at the response to silicon. You can look at the response to mercury sulfide, perhaps. Some of the more common responses. Carbon black is a good example. The sources of carbon are enormous on the planet. Everything from soot, basically lamp soot, to coal tar, to burning of animal bones to get basically ivory black, the equivalent of ivory black, waste ivory black, if you will. And one other comment I can make here on having intensively worked with this Raman instrument for a long period of time, for over 3 years now, and have done research on a number of philatelic items, perhaps over 300 different items. The instrument is best used when augmented by X-ray technology. Why? We can take a red cancel and determine that it contains sulfur and mercury. So we put the two together and say, okay, it's mercury sulfide. The Raman spectrum for mercury sulfide is known and is clear. And indeed, we can then take the Raman spectrum, the data we have from XRF, and we know exactly what we're dealing with. In the case of carbon black, another good example. If I use the Raman instrument for bone black or coal black, I get these identical G and D peaks in the same waveform. As a matter of fact, what I did in selecting Renishaw is I actually took covers, 2 covers, inexpensive covers. And by the way, both of these covers are available on eBay or equivalent sources or through a flea market for less than $15 a piece. We're not dealing with great rarities here. We're dealing with ink. There are very few ink collectors out there. But it's the underlying understanding of what was used at the time which allows us to do expertising if we want to. I can prepare a library of known cancellations on stamps, cancel stamps that have CDS cancels on them. Good example might be China, large dragon or small dragon stamps. Shanghai, 1880, April, May, June, July, August, and I can watch the involvement of the different cancellation substances or molecular compounds that were used. I then can expertise. And the obvious expertising that would occur would be if, in the case of Beijing, or then known as Peking, custom Peking, their blue ink, if I determined that that was Philately blue, which was invented or created by Dow Corning in 1931, it's obviously a forgery. So some things are obvious. But getting back to the coal carbon.
Just a quick question. Have you published the work on the China?
No, I have not. I have published some, but I have not. I have published through the Asian philatelists quite a bit, actually, but not specifically using this instrument until recently. I did, there were, in this year's Asian philatelist, I do have an article comparing the VSC 8000 with these two covers, as a matter of fact.
I've got other questions in the queue. If that's okay, I'll interrupt you where you are, and let's get those moving here. The next one in the queue is Mr. Barwis, and I need to go find him and then get him, allow him to talk. There we go. John?
Can you hear me now?
Yes, sirree.
Okay. I'm just curious about what makes the two color shades different, given that they have the same chemistry.
It's really a good place to go to answer that question, and it's really beyond. I'm not sure I can give you a good valid answer. A good place to go would be to a dye maker like Abbey.com, which is online, and type in crystal violet. And they have a description of, they describe crystal violet as teramethyl, hexamethyl, and pentamethyl combinations, which in turn generate a kaleidoscope of colors. And they have on their website the colors that one can obtain, from a deep blue to a bright violet to almost red color, by mixing and matching different tetramethyls. And these are different carbon, hydrogen, nitrogen combinations that are mixed with chlorine.
Okay, great. Thank you.
No problem.
Next question comes from Mr. Morrell.
Good morning. Mr. Kravitz, you mentioned Prussian blue found on the Rochester cover. I didn't quite follow that after it. Which marking was it that you believe was Prussian blue, and how did you ascertain this?
All right, let me go back to that point if I can. Hang on just a second. I seem to be frozen. Okay. What I did, basically, let me back up for a second, okay? Prussian blue was commonly used in the 1850s around the world, okay? And it was used into the 1890s in certain parts of the world as well. After the turn of the 20th century, Prussian blue was discontinued in places like China and other places in the world. You can buy Prussian blue samples from Millipore Sigma, and you can run a Raman spectrum. You can also Google Raman spectrum Prussian blue, and up will come the spectrum that you see in the paper, which I would show you if I had the ability to show you. Right now I seem to be frozen. I'm not sure why, but I am. Okay. And I'm leery to move it. that spectrum has a peak. It's, as I indicated to you, it's a nitrogen, cyanide, ferrous compound with a peak at 2153 and two smaller peaks, and then very low Raman shift peaks in the range of 300 to 500. And the waveform is online, readily available. And if you have access to a Raman spectrometer, of course, you can obtain a sample and run your own. But obviously, it is what I show you there. All right. Now, am I answering your question? I'm not sure what your question was at this point.
Yes, I wasn't sure if you had, I must have missed it. So you actually ran a sample of pure Prussian blue, and you determined that it was...
That waveform is mine from a sample from Millipore Sigma.
And it matches one of the peaks, at least one of the peaks that you observed from one of the markings on the envelope.
No. This Prussian blue has nothing to do with the envelope. It has to do with the reflection on the color used by Rochester in 1894. One can look at that, the observer, the collector of postal history, looks at that and says, aha, that must be Prussian blue. But it's not. In other words, what I'm really trying to infer there is that it has no relationship to the cover.
Got it.
But okay.
Yes.
The color is the color, and Raman is not color sensitive. Raman looks through the color. Could care less what the color is.
Right.
Now, if I were using a VSC 8000, interesting point, and I was sweeping laser from very low wavelength to very high wavelength, I would get completely disparate responses. I would get such a difference in response between the Rochester cover and the Topeka, Kansas cover, or the St. Louis, Missouri cover, as to say one was definitely a forgery or not the same, a different ink or dye was used. Not true. And the genesis of the paper that I present in the Asian Philatelist, and by the way, that paper was already published this spring in the Collectors Club of New York, gives you research done using Dr. Smith's VSC 8000 at the Smithsonian. A member of the BPA carried those two covers, the covers that I present here, to the Smithsonian, and they were tested, and the data was recorded. And this paper in Coming Asian Philatelist is unfortunately in Mandarin, but if you want the English, you can get a copy from the Collectors Club in New York. They'd be delighted to send you for a nominal fee.
Okay, thank you. And I get what you did now. And please repeat the name of the website where you get information about them. ABBEY.com, Abbey.com, two B's. Okay, got it.
Go there and just search Crystal Violet, and you'll be delighted with what you find.
Thank you. I'm sure I will.
All right, Mel, let me go on to the next question here. Cynthia, you are up. Cynthia. Oh, wait a minute. I pushed the button. There we go.
Can you hear me now?
Yes.
Okay, great. Thank you. Mel already addressed the answer to this question in his analysis of the Chinese postal history and the dragon markings. But my question was, could you please talk briefly about the implications of this kind of research on the analysis of postal forgeries?
Yes, that's an interesting question, and obviously it has great bearing on the detection of forgeries. If we have to build, the genesis of the real use of the instrument is to build a library in an area of research that we want to do. Now, I mentioned the fact that large dragon stamps or small dragon stamps, if we acquire inexpensive examples, and by that I mean damaged examples, used examples that are CDS canceled. So we can't use a seal cancel when it comes to Chinese custom post stamps, because that seal cancel gives us no indication of the date of when the seal was applied. And obviously it's easy to falsify a seal. When it comes to red cancels, or it comes to, let's take the case of a blackish or blue-black cancel. We could be dealing with ultramarine, which would be synthetic lazurite, azurite, another compound, a whole host of different carbon black, a whole host of different compounds could be involved. It's important that we pick a stamp that we don't want to acquire stamps that are very, very expensive. So a stamp that's half a stamp, but as long as we can read 1882 and the month, April, that's good enough. And if we can acquire May 1882, June 1882, and so on through the year 1882, at a given post office, we also need to know if it's Shanghai, Peking, Tianjin, or where, Taku, where used. We can then build the library of a known goods. No one's going to forgerize a damaged stamp, a stamp with obvious thins, missing perfs, etc. We can use that library database to expertise expensive items. We can catch forgeries easily by simply getting a Raman spectrum and comparing it to what it should be or what it is in the literature. And if the dye was developed in the 20th century and it's a 19th century cover, then obviously it's a forgery. I mean, it's that simple. Out of the box, a forgery. And there are many, many examples on eBay of Chinese material that are forgeries. I have been personally collecting Chinese postal history for 25 years now. And before that, I had a large collection of U.S. postal history as stamps, including a Colombian stamp collection and a Trans-Mississippi stamp collection, which I sold years ago through the Siegel Auction House and represented by the Colombian Stamp Company. I hope that answers your question.
Thank you, it does.
Okay.
All right. Thanks, Mel. Let me get Cynthia out. And the next person to come in is Van Siegling. Van, are you there?
Yes, I am. Okay. My question involves the availability of these machines. Do you know if any of the philatelic organizations, such as APS or the National Postal Museum, or maybe the Royal over in London, might have these machines?
This machine is the Metropolitan in New York City has 4 Renishaw machines.
Okay.
I know that for a fact. I don't think the Smithsonian National Postal Museum has any. I know that the Philatelic Foundation has none. I know that the Royal does not have any. And of course, the VPA relies on personal expertise, and they're quite good at what they do. And I have, by the way, I can mention, from time to time over the past 2 years, supported the VPA when color becomes an issue.
About how much do these machines cost? You have an
The
idea?
machine you're looking at here on the screen where I'm locked up, okay, is a mere $380,000 with 3 lasers. And by the way, the machine sits on a table. I'm not sure you can see that table correctly. That's a Tor $5,000 vibration platform. We're dealing with such a small amount of photon collectivity as inelastic scattering that when a truck passes on the highway outside, I get enough vibration to cause enough noise pickup to abort my work at the moment on the screen. This is a vibration sensitive platform. Cosmic ray interference is another issue with the very sensitive CCC detector. And the machine software has a zap feature. The software is excellent. I mean, I've used lots of instruments in my time, and this particular machine is superb. I should also mention to you that in the beginning, when I looked at acquiring a Raman instrument of this type, I sent 2 postal history items, inexpensive, $15 covers, to Crooker, to Hariba, and to Registry. And I asked them to look at the carbon ink, the carbon cancel ink. Brooker came back and told me I was dealing with ivory black. Hariba came back and told me they weren't quite sure what I was dealing with. They would need more time and effort and energy. And Registry told me that it's indeterminate to tell me what I'm looking at because the coal black Raman spectrum and the carbon black spectrum are for ivory black or bone black are identical, and that they would really need to subject my samples to X-ray fluorescence to find out if there was phosphorus present. This is a good example of where no one instrument can give you an exact answer. Raman will tell you that the spectrum is carbon, and you can match it to ivory or you can match it to coal tar black. However, yes, go ahead.
Go ahead, Mel.
I was just going to say that by using XRF technology, if you can eliminate phosphorus in the element response, you know that it's coal tar. So you close the circle by having more than one technology available to you. There's no magic technology.
If those of you participating have been watching, there's been some conversations in the chat room. The VSC 8000 is the only equipment available to the public in the Smithsonian. They do have the Raman technology available, but it's not available to the public. And after hearing Mel describe the potential eye damage and so on, and the cost, I can imagine why it's not available to the public. I've got one more question for you. Let me get him up so that he can talk. Where'd he go? Looks like he has signed off. We had one person asking why the data doesn't allow us to tell the color.
Why the data does not allow us to determine the color?
Yes.
Because the molecular bonding structure may be a function of pH alone. In other words, color may be a function of pH and not a function of the molecular bonds. We're looking at bond resonances, the energy absorbed by a bond, a carbon-hydrogen bond or a mercury sulfide bond. In cinnabar, mercury sulfide, of course, is cinnabar. You can obtain samples readily available, again, from any of the chemical suppliers. A good place to go for carbon samples would be some of the paint manufacturers or ink or ink. When I talk about paint manufacturers, I'm talking about artistic paints, not house paints. Those who provide samples of Shugart, different forms of of carbon black. Any other questions?
I don't see any. Danny Brinkling was asking whether or not there's an XRF in the Smithsonian, and the answer is that it no longer worked and it was not replaced.
Okay, I think most XRFs, including the Philatelic Foundation, are basically tracer instrument and are limited to heavy elements only. If you want to look at light elements, you need to get a much more sophisticated, like a Horiba XGT 9000, which has a light element detector, which becomes very important if you're looking at the details of sodium, for instance. You can use helium with some of the less expensive to look at sodium, but you can actually look down to carbon with the XGT 9000 Horiba instrument. So there's a lot of technology available, but again, it's pricey.
Yep.
I think the marketplace in general, as time goes on, the Roman expression caveat emptor could not be truer today than it was 2,000 years ago. Personally, I got involved in this area simply because I was offered very expensive Chinese items by well-known philatelists that were forgeries. And it's a means of protecting myself.
All right.
That's about it, I think.
That gives us about 5 minutes before it's Tony's turn, and that gives everybody a chance to stretch their legs and take a nature break if they need it. We will start again in about 5 minutes at 11 o'clock.
Hey, Ken?
Yes.
Sorry to interrupt. Just one real quick question. So, Mel, you purchased the Raman instrument basically just to support your hobby?
I'm sorry?
You purchased the Raman instrument to support your hobby?
The Raman instrument supports my intellect.
Okay.
My hobby supports my pleasure.
Okay, perfect.
I have a need to know. I've always had a need to know. I have several patents and have been involved in research all my life. So this need to know drives me through the ocean, so to speak. And I'm not satisfied unless I know the genesis of what I'm looking at. It's a terrible habit I have.
I understand, but thank you very much.
Excellent
presentation.
Thank you.
Thanks, Mel. And will you please unshare your screen? And
yes, I will do that. I'm gonna unfortunately have to.
Hang on. There.
Okay, you unshared me. Thank you.
Yep. Thanks again, Mel, and we'll reconvene in a few minutes here.
Thank you so much.
Hi, Tony.
Hi.
We'll get going in just a minute.
That's great. Tough talk to follow. That was really super interesting, wasn't it?
Yes, it was.
Do you see my presenter's view or the
you have shared your screen and I see your slide.
The full slide?
Yes.
That's perfect then. That's lucky. 50-50 chance.
Yes. All right, it is 11 o'clock. Let us start again.
Okay, thank you.
Let me introduce you first here, Tony. Our second presentation is by Tony Thompson. And actually, I assume you're sitting in Canada today?
I'm in Stockholm, Sweden.
Oh, you're in Stockholm. All right, so it's late in the day for you. Tony started recollecting stamps in 2003 when he moved to Halifax, Nova Scotia, to work with the Northwest Atlantic Fisheries Organization. Naturally, his collecting interests centered around the cod stamps of Newfoundland. He did well in one-frame exhibits in Canada, winning golds, but moved to Sweden in 2010, where the interest in Newfoundland exhibits was less than tepid, and he stopped exhibiting. Tony enjoys writing articles of an analytical and scientific nature, received the BNAPS, the BNAPS Vincent G. Green Award in 2013 and 2021, and the CCC Colonel Pratt Award in 2011, 2013, 2018, 2020, and 21, all for articles in BNA topics. His interests outside of philately include cycling, extreme macro photography, and bird watching. So with all of that, we're still going to talk some more about Newfoundland's royal visit stamps. Tony, take it away.
I am, and thank you very much for the introduction. And this talk isn't actually about cod stamps. I think I'll run through the whole presentation first, like the last presenter, and then take questions at the end, if that's okay with everybody. I want to talk today about some work I've done over the last 2 or 3 years using a readily available scanner to look at the color analysis on postage stamps in an attempt to move away from the very difficult task of just eyeballing colors and putting stamps into different piles. The other thing that really attracted me about using a scanner is it's something, a piece of equipment that we can all more or less afford, and it does give you some scientific data by means of numbers related to the red, green, and blue content of the color. Unlike things like the VSC 6000, 8000, which gives you a sort of frequency plot of wavelengths, harder to interpret and also much, much more expensive. So scanners are all under $1,000, where the VSCs 6,000, 8,000, I think, are $100,000 upwards. So this is a tool that everybody can basically use at home. It also really struck me the amount of work that had been done by the IOP in its previous symposia, and there are many articles on using scanners, and they have a little bit mixed results. So I wanted to see if I could myself get results that I was happy with, and perhaps give some ideas about different ways to use scanners or different setup procedures, which may make results a little more meaningful. This presentation is very much a methods presentation. It doesn't really end up with any firm philatelic conclusions. Let's just move on. There we go. So these are the stamps that are in question and that I've worked with. It's a very common stamp from 1939, printed in New Malden, England, and then issued without a surcharge. The basic 5-cent stamp was issued in Newfoundland in June 1939. And then in November, there was a shortage of 2 and 4 cents regular issues. So they applied a red surcharge to the 5-cent stamp, and they produced more 2 cents and 4 cents. In this talk, I'm only actually going to talk about the blue ink. I'm not going to go into the red ink, which is in the paper, but just not in this presentation. Likewise, in the paper at the end, there's more of a comparison between my results and results obtained in previous IAP Symposia issues. And again, I haven't focused on that in this presentation. It's embedded within the talk, but I haven't separately identified these comparisons. So that's really up for people to go to when they see the symposium proceedings. And then just to say that these are my way of interpreting things. There are plenty of other options and plenty of good examples in the previous IAP Symposia and elsewhere. There is in existence a rare aniline variety in which the blue ink has basically run to the back of the stamp, and it also runs around the front of the stamp around the blue lines. So it gives this typical aniline effect. The sort of philatelic question here, and I shall also discuss this next week in a presentation which is really stretching my intellect. I'm not a physicist, I'm a biologist that works on cod. So some of this equipment is a bit tough for me to explain. This is a close-up of the stamp and the surcharge. The blue ink is very precisely laid down, and there's no bleed into the white paper. The red surcharge is a very clear red surcharge. The blue ink is printed by the intaglio process, where the ink is quite thick and paste-like, and it's put into basically lines on a metal plate, and then the paper is pressured or forced into these lines, and the ink and the paper move in and give a raised profile to the stamp. And you can see that on the bottom section there, where the blue ink is raised out from the paper. The red ink is done by a different process, and that just sits on the surface. And I've shown that here with the thin red line. It's just on the surface. The basic equipment and software I used for this analysis was a basic but quite high-end scanner, the Epson Perfection V850 scanner, which in the image grab here from Amazon.Canada claims it's almost $2,000. I bought this for closer to $1,000. I'm not quite sure if the price has gone up in the last few years. It's an expensive scanner, absolute fraction of the price of a VSC 6000, 8000 machine. But still a bit of an investment, and very much more than most people would have in their home. And later in this paper, I'm going to compare results from this scanner with other scanners. The scanner was calibrated using a reference picture, which is quite useful, and it keeps the scanner constant over time. You can scan all scanners if the software allows with one of these sheets, but it doesn't allow you to compare results across different scanners. It's very much within a single scanner. The software that I used was independently available ViewScan software, which allows you a lot of control over how the image is scanned and what filters are turned on and off. And I'll talk a bit more about that later. We then have this absolutely wonderful ImageJ software, which is freely downloadable and can do a wide range of analytical techniques to do with red, green, blue images. It begins to require a little bit of analytical expertise to use. So we're moving a little bit away from very basic picture examination to something where a little bit of a background in statistics or physics may be very helpful. And then a lot of the results have been analyzed using Microsoft Excel and a macro that I wrote to help me do that analysis. Again, the better you are at statistics, the easier you find this sort of work. So there's no question that using a scanner to look at colors does rely somewhat on the analyst being able to do fairly simple software and use fairly simple programs and maybe even program. The scanner setup. It's calibrated. I scanned all my files as TIFF, which is a lossless format. This contrasts with JPEG, which is a common format where you do actually lose information. So I preferred to stick with the lossless format and actually file sizes that are considerably larger. So there is a little bit of a trade-off doing TIFF, but at least you're getting the scanner RGB signals as they come out of the scanner and not reformatted to JPEG files. And then turning off all the scanner enhancements. And on the right here, I've just shown you some of the scanner enhancements that you really need to turn off that would alter the color balance and the colors to some degree or other. Then one of the toughest things to appreciate is the auto color balance and auto exposure that's present on many scanners, and often something you can't turn off. With the ViewScan software and the scanner that I used, it had the ability to actually lock the color balance and the exposure between different images. And I've just shown you at the bottom here 2 scans with a grey card, which was all the same color, and different backgrounds of either white or grey or colors, be it pink or purple. When you do the scans on a scanner which has the auto adjust on, the grey card comes out looking different colors, 4 different colors, lighter or darker, depending on the background. When you lock the color, the grey card comes out all the same, which it is and it should be. I got sent a lot of scans of some small screen stamps from a colleague, which were stamps on a black background, different numbers of stamps per page, and actually the auto exposure basically meant that these were useless for looking at RGB color. So turning off all the enhancements and checking the autos are also turned off. Okay, I'm now going to move a little bit more into the researchy side. Surface reflections and ink thickness is definitely a problem when you're doing this sort of analysis with color. On the left-hand side, there is a 1200 dpi scan, so quite a high resolution scan showing the type of image that you would get out of a scanner, which is, of course, pixelated with light and dark areas and areas of color. If you photograph that area, the same area as the one on the left, you see that there's considerable structure to the blue ink. And you see light and dark areas where the ink is thinner and thicker, which comes out as basically the color being very pale or almost black. You can also see, and particularly on the right in the enlarged areas, quite severe reflectance, especially with these intaglio inks. They have a very reflective surface to them. This is unfortunate, and I didn't find a way to remove these reflections. It might be possible if you sort of embed your stamp in cooking oil or something to remove this reflection. I didn't go that route. But you have to work with kind of what you've got, and these light and dark areas and the reflectance is just part of the package. A tiny bit about RGB values. I think most of the participants today probably know this sort of thing much better than I do. But if you scan an image, it's made up of tiny square pixels, as you can see on the right. And each pixel has a red, green, and blue color value. And these range from 1, which is no signal, dark, to 255, which is a very bright color. So just as an example, white reflects as the RGB values being 255 for all of them. Black is 000. And then all the shades of grey have the red, green and blue value the same. So they come out looking like that. Red is one of the pure colours, so you get a red signal and then nothing in green and blue. Yellow's a mix, so on and so forth. And on the right, there's just an example of the RGB value for something that looks red, but it actually has quite a lot of green and blue. And that indicates that there's a sort of grey flavour to the colour. And then here, the blue colours are just a little bit more blue, but it's a mid-tone in its lightness. So a lot of the other pigments in the other colours in there to give it the sort of grey value. The RGB analysis itself, I looked at TIFF images. I also explored the various color models, and I separated on this hue, saturation, and lightness color model, but found it awfully difficult to interpret what it actually meant. The hue I could understand, it's effectively a wavelength of light. Saturation and lightness, I find it didn't really help me. And when it comes to the analysis, the HSL model is a nightmare. It's a mixture of a circular radians for hue and then percentages for saturation and lightness. So all the presentation really from now on, I think, and the statistical analyses is done on RGB values. These can be plotted separately as averages. There's frequency histograms you can see on the right, which gives you an idea of the variation. And they're amenable to any form of statistical analysis, really, including more multivariate analyses. This is another slide in a bit more detail of the HSL color model. I was thinking this would be easy to interpret, but to me, it just wasn't. As I said, the hue is a circular thing which kind of gives you the wavelength, and then you get the saturation, the amount of grey, and then the lightness, the amount of white or black. I could never really interpret this. It never made sense to me. I could look at colours with different amounts of saturation and lightness, and I couldn't separate them out. It didn't help. Right, moving on. So this is an example of the results from a blue inked area. The top of the signals with the frequency histogram that you get from the output and the various pixels shown in shades of grey for the 3 different colors. And then you can get average values coming out of it. And I found just the average RGB value the most useful one to use. And bearing in mind that the raw data is a frequency plot, but I never got into analyzing the scatter, the standard deviation of the plots. I just kept with averages, and that seemed to work pretty well for me. I put this slide in partly for information, but there is a statistic, a number that you can calculate called the red mean statistic. It's shortened to delta C, delta meaning the difference between 2 values. And it's basically a measure of how far these values are apart in 3-dimensional space. And it's a little bit like Pythagoras' theorem, but with an extra axes thrown in. So you can calculate the square root of the sum of the squares. You come up with a delta C value. If the colors are similar, the delta C value is quite small. If the colors are far apart, the delta C value is quite large. And this is a simple way that could allow you to compare different clusters of colors on stamps. It's probably the most easiest statistic to use. I then went on to try different scanners. So as I said, the base scanner used in most of these other slides was the one on the bottom right there, the Epsom V850 flatbed, which is running on $1,000 to $2,000 to buy. And then comparing it with an old Canon flatbed I had, the 8800, and then a laser printer that had a scanner attached and an inkjet that had a scanner attached. And the important thing partly to realize is that when you look at the picture of the stamps, possibly with the exception of the PhotoSmart, they all produce realistic images of the whole stamp. They all look as if they're quite a good scanner. However, when you magnify up the image and you start to look at the individual pixels, you see there's really quite a lot of difference between the scanners. The all-in-one scanner on the top left has obviously been processed. There's something funny going on with this image, even though the enhancements were turned off. This is, or looks to be quite clearly, a processed image. And you can just imagine trying to analyze that blue area on the right. The colors are all over the place in terms of their density. There's a strong edge effect. It looks like it's been focus sharpened. So I was unable to turn off the enhancement on this scanner. The other 3 are quite good, but you start to get a much smoother, almost blurred looking image on the top end scanner. And I think one point to realize is that images that are not enhanced do come out looking much more blurred. The scan that you see in the pictures which has had enhancements are usually artificially sharpened, like our mobile phones happens. So you do see differences in the magnified images. And this really led me to believe that the top end scanners do produce different results to other scanners costing $250 or less. I also looked at scanner resolution, and this varied from 300 dots per inch, which was the lowest level I used here, right up to 4,800 dots per inch. with the Epsom scan, the Epsom scanner. And the summary is that actually the lower scan resolutions, they don't alter the colors that you see at all. What they do is enhance edge effects. So if you look at the 300 dpi, there's a lot of a bigger unclear boundary between the blue and the white here, and also between the white and the red. If you go up to the 4800 or the 2400, you get a much sharper boundary. So it just means that whatever image you start analyzing, so I would only analyze a very small part of this picture on the right, you just get more pixels of pure color, and they're not affected by the other boundaries. And then just really to show you how poor a scanner is compared to a photograph. The photograph is 20 times the resolution of even the top-end scanner. The problem with photography is you really can't balance it between pictures. These were taken with flashlights, and the flash guns are notorious for different color balance between each flash. I then went on to look at background effects, and John Sibulkis sent me an email yesterday and made a very valid point that sometimes this really depends on what you're trying to do and what you're using. I found using a white background, the colors were just a little bit more vibrant, but it didn't really give you any difference in comparative results. These were just slightly lighter RGB values than scanning on a black background. But if you did an analysis comparing stamps, it wouldn't matter which background you used as long as you were very consistent, and consistency is key. John made the point very valid that he wanted to separate out postmarks which are black, so a black background made much more sense. So I settled later just to use a white background, mainly just for consistency. It didn't really affect the comparative results. Areas analyzed and the ink density. So this is a typical stamp that I worked on, and I looked at the ink from 3 different areas, which I called A, B, and C. And what I found was that if you just look at the ink from the frame line, which is the top left red circle and the left-hand image at the bottom, you get a lighter value. If you move to an area of dense ink, like in areas C or perhaps B, you get a much darker value. And the RGB values, they're not simply a question of each value going up by 10% or 20%. There are slight differences in the shifts of the red, green and blue. But whatever you're doing, it's incredibly important to use the same area in your analysis. So that's absolutely vital. And you're still going to get difference in results as to whether the stamp has been lightly printed or heavily printed with the same ink. So there are problems that you could run into that are unavoidable. I then wanted to know if you could use the RGB values as a proxy for what you and I would describe a stamp as in terms of color, or what the albums, stamp catalogues, described as a color. So we see, just looking at the blue surcharge, the middle column, for 4 different stamp catalogues, we get basically a couple of different colors, really: violet, blue, ultramarine. And then Stanley Gibbons changed their description of the color to deep ultramarine. You have 2 other catalogues which call them violet, blue and deep and ultramarine, but you've no ideas if these are the same color as those above. So it's really difficult to know what color catalogs are using. And I think Stanley Gibbons is a little bit random, even with its use of color keys, which came out a long time ago. It's really difficult to know what colors they are talking about. So kind of on the face of it, an RGB value may be better to use. And this is a slide which compares, again, visual comparisons, a stamp with known color keys. And these color keys have been around for a very long time. In the 1930s, Stanley Gibbons used color keys by showing a whole lot of different printed stamps. These were actually not printed by the intaglio method. They are printed lithographically. So you actually would expect a different color because they have different reflectance properties. The current color key is printed on plastic paper. And again, its printing methods differ to that seen on a stamp. So you may expect different colors just because the stamps are printed in a different way from the color key. But you can take RGB values from each of these colors, and I did that, and I'll talk a bit about that later. If you do a visual comparison, you see that the stamp on the left here, the normal stamp, which is the left-hand side, you look at the color key, and it comes out, to my mind, as deep violet blue. That's, to me, a pretty good match with the ink that they used, and that was my visual pick. If you then look at the color charts for deep ultramarine, ultramarine, and violet blue, they're nowhere near what the catalogue described them as. So, to me, none of the catalogues are following the Stanley Gibbons color coding, even though they're a Stanley Gibbons color key and a Stanley Gibbons catalogue. When you look at the aniline stamp, and remember I mentioned that the blue ink bleeds into the white paper, it becomes very difficult to actually visually assign a color. The blue run gives the stamp a different opinion, and I picked out chalky blue visually, but you can actually see that this is a bit of a combination between the dark blue, which actually looks the same color as the normal stamp, and the much paler bleed ink areas. So visual identification is very difficult. I mentioned before that you can use the red, green, blue value from the stamp, which is the top line in this table. So this is the blue ink of a normal stamp. It gives a red, green, blue value of 59, 73, and 78. You can do the same with the color keys, and you get these different red, green, blue values out. So each Stanley Gibbons color key, I scanned and assigned it a red, green, blue value. And using the red mean statistic, you can match the best fit from the color key to what the stamp is showing. My visual pick was not quite the same as the lowest red mean value. The lowest red mean value came out as indigo. My visual pick was deep violet blue. But you see the red mean statistics are actually quite similar, 35 and 39. Even though the indigo and the deep violet blue do look a bit different. Then some of the other colors that the catalogues gave were a long way off. So I think there is some value in using the RGB values to help you match to a color key. So I found that quite useful. The objective comparison, one of the problems is that when you and I look at a stamp with our eyes, we don't see it in the same way that the scanner does. The scanner shines a bright light, and then it's focused onto a sensor which goes through some digital electronic processes. So what the scanner sees is absolutely not necessarily the same as what your eyes see. So I could well imagine a situation where you can group stamps visually, and the scanner may well give you different groupings just because it sees things differently. So the fact that it might not be the same as visual may not be a problem with the method. I would like to hope that if I separated stamps visually, I would get the same separation on a scanner, but I haven't yet tested a scanner with that many stamps, but I will do in the future. This just shows some of the typical variations. So this is the same block of 4 stamps. And if you scan the different lines, A, B, C, you do get within and between stamp variation. So even though these were obviously printed with the same ink at the same time, you're still getting some variation. And if you look at what the red mean statistic can give you, you see in the second top triangle, which is area B, it all comes out as chalky blue. If you look at the frame line, it comes out as slate violet, and then the bottom one, mostly indigo with some blue black. So there's some variation, but it's not so very much. So this also gives me confidence that the method can work with a scanner. I did some comparisons between blocks printed on 2 different papers, and I'm indebted to Richard Judge, who's participating here today, for some of the more complex analyses using various instruments. And he identified 2 different types of paper. A paper which contained barium only, and a paper that contained barium with titanium. And I'll talk much more about this next week. And then there's the aniline block. So if you take the RGB values, you see the average values are here on the left. If you do scatter plots of the values from the stamps, you get much more data to compare. And you see that the red, what are these, rhombus squares, tend to be brighter, lower in RGB values than the other 2 blocks with barium only and barium and titanium. So the red, green and blue analysis, when you plot it graphically using actually this wonderful software called Kate, which is freely available on the web for download, an add-on to Excel that allows you 3-dimensional plots. You can look at these and almost in a visual way determine differences. So the aniline block is a little bit lighter, and maybe we would expect this if some of the paler color is bleeding into the paper. So that's an analysis that can be performed. So I just have 2 slides of conclusions, which may act as a focus for discussions. I believe that you need to use a professional level scanner if you're wanting to do RGB analyses of stamps. I think using the low and mid-level scanners is unlikely to work because there's more noise in the signal. The scanner software must allow for the enhancements to be turned off, very much including this auto exposure and auto white balance, which actually seems to be one of the harder to turn off. It's best to calibrate the scanner for color so you can see that it doesn't drift. I scanned at 1200 dpi, which is a much larger file, but when you zoom in to the blue ink parts of the stamp, it gives you sort of 30 by 30 pixels instead of 5x5 pixels. So it allows you more data to analyze. The area of the stamp being scanned should be the same. And the final slide is that, unfortunately, anybody doing this approach really does need to have some basic familiarity with data manipulation, statistics, and graphics. We can't really get away from that when we start dealing with real data, which you can make objective analyses on. There may be a difference between the RGB analysis and visual groupings. Different printing methods can give you very different results, even for the same color, mainly due to this reflectance problem, I think, and the way the ink is laid down on the paper. The results are quantitative and objective. So they're scientific results, if you like science and are used to dealing with scientific information. They're not human guesses, and this is a real problem with identifying shades. And then I believe the red mean statistic may be useful in helping you to compare colors. Okay, thank you, Ken and other participants. That concludes my presentation.
Thanks. Thanks, Tony. I actually have a question already, and that is, can you talk a little bit about the camera that you used?
Okay, yes, the camera was a, first of all, it's not in any of the RGB analyses, so this is a bit separate from the talk, but I'm happy to tell you about the camera. It's a Canon 5D with a 200mm tube lens, and at the end of that is a microscope objective, probably a ×4 or a ×10, I think, with these, illuminated by 2 flashlights from the side, and it's all set up in a very strong metal frame. Vibration is a real problem, but the photographs you get is incredible, and this goes all the way up to a 50 times long working distance objective. So a lot of fun using the camera, and a lot of insight for looking at the structure of the ink and the way it's laid down on the paper. And you can even identify improperly or poorly dissolved, well, dissolved is the wrong word, poorly dispersed pigments. So I did an article with an artist, John Reisman, and it was fantastic to work with an artist, because they view colors as part of their livelihoods, really, and have a very different view of it. And it was really interesting just to discuss the different pigments and the way the colors look, and how he could quickly make with watercolors any stamp color. Amazing talent. So that's the photographic equipment I use for those.
Thanks. Does anybody else have a question? Please submit through Q&A. Or if you're a presenter, you can just speak.
Tony, I have a question about aging of the scanner as time rolls on. How would you compensate for that?
I mean, I think the only way would be recalibrating with the standard color charts, which would allow you to hopefully set the scanner back to its kind of original specifications, in the sense that at least it would be recalibrated. All of my work was done on a new scanner within probably 6 months of purchase, so hopefully that doesn't affect it. But the other scanner I replaced with the Canon flatbed scanner, which was still a nice dedicated scanner, but that had really failed. The red color balance on it was way off. So I think just regular calibration with the scanner. And I guess you could tell if it's actually moved away from its original calibration information as well by looking at the images.
And let's see. Let me get this person in. Oh, we've got several questions coming in here. Good. Bruce, you are next. Mr.
Hi, Tony.
There we are.
Hi. Hi, Bruce.
Hi. Thank you for this. This is really fascinating. I've thought similarly that we could do a lot with scanners without requiring the more massive equipment that the expertisers use. Mm-hmm. I was unaware of the Epson 850. I've been using for some time the Epson 600, and I've been a little bit frustrated by my inability to make adjustments to it, maybe because of lack of knowledge or one thing or another. I wonder if the ViewScan software that you suggested would interact with an Epson 600, perhaps as well as the Epson 850.
Yeah, absolutely. There's two big advantages in the ViewScan software. One, it works with virtually all scanners, including those scanners that have out-of-date software that won't run on the modern operating systems. So should you have a 12-year-old scanner, the ViewScan software will have a interface that works with it. So absolutely almost any scanner it will work with. The other thing is how much you can manipulate the enhancements with that ViewScan software, and you have to buy it. It's an independent. It's not a free download.
Sure.
You buy it as a annual fee, or I think it's always an annual fee, and it comes in different versions. And I have the top pro version, and it's not that expensive either to buy.
Right.
The V600. I think the scanner is almost identical to the 850 in what it can do from what I read, actually. You just save an awful lot of money by buying the V600. So as far as I can tell, it's a fantastic scanner.
Yeah. Well, I'm a loyal stamp collector, adhering to many of the preconceptions people have about us. So I, not only was I unaware of the 850, but I was happy to have a more affordable option.
Yeah.
Thank you very much, Tony. Appreciate it.
Absolutely.
Next up, Mr. Morrell.
Yes. Could you hear me?
I can.
I wonder, you referred in your presentation to 1200 dpi. I wonder if you get similar results if you use a 2400 or 4800 dpi, or would you get more precise reviews or not?
Yeah, no, that's a great question. So I have on this slide here the images from scanners used at 5 different DPIs from 300 right up to 4800. 4800 is stretching it for my scanner. 2400, it can certainly do a resolution of 2400, maybe a touch more. The 48 is stretching it. If you look at the area in the middle of the red, for example, the surcharge here, the RGB values are the same for whatever the resolution you use across the whole lot. So the resolution doesn't affect the RGB value if it's an area of pure color. The difference is when you look at edge effects. So again, if you look at the edge effect between the red and the white, for example, the paper and the red surcharge, you see there's this boundary layer where it goes from red through various shades of pink to white. That becomes much harder to separate out when you do your analysis. So I would open a TIFF file up in a software Photoshop kind of package. I would crop it to a red or a blue area. So with that red area in the middle, I would crop it just so that it includes the red TIFF image, which would be maybe, well, actually, if it was the 300 dpi scan, it would probably be something like 3 by 5 pixels, because going outside of that, you start getting these edge effects. If you do the 1200 dpi, you can see you can get like 30 by 30 pixels quite easily in your cropped image. And it's that cropped image that I feed into the ImageJ software that separates out the TIFF file into our red, green, and blue matrices. So the scan resolution doesn't affect the RGB value, but it does affect the ease on which it's used, really. So that's why I settled on 1200 dpi and nothing lower. And if you don't have these big areas of color, which some stamps you're really struggling to get big areas of color, you can go on to some of the lines, and again at 1200, you would be getting a line that may be 8 pixels high by 30 pixels long. So you get a decent sample size to work with. Of course, the lower DPI does give you an averaging effect built into the image. So you sort of have averaging. But I hope that's answered your question.
Yep.
Thank you. And John, I have figured out how to allow you to talk.
Does it give it here?
So you are up next. You need to unmute.
Did that do anything?
There we are.
Yeah, hi. I didn't actually have a question. I didn't have a question, Ken. I'm actually just saying that I can't use the Q&A, which I'd much rather use because it's less intrusive. So I don't know if there's some setting or whatever it is.
No, Yanni, I'm sorry, Yanni. I'm talking to Mr. Cebulskis.
Okay.
Oh.
I hear you.
Yes, John, you want to ask your question?
Oh, okay. My question was just if you could give me a source for this red mean. I've never seen it before.
Okay, that in itself is interesting. And thank you ever so much for your email yesterday and all the comments. It's very relevant.
I hope you took them in the right frame of mind.
Oh, yeah.
I thought about it and I says, I hope I'm not going to make an enemy here.
Not at all. No, absolutely.
I really did appreciate your paper.
Not at all. I just hope it's sort of moving things on. I think the real challenge is stamp collectors, or I guess people in general, fall into those which quite like mathematics and people which don't. And if you don't like mathematics, some of this analysis with red, green, and blue colors would become quite difficult. Answer your... Sorry, go on.
Break in for a second? You see, my background is mathematics and computer science. So I don't think anything of writing programs to do specialized things to analyze the colors and stuff. And that is obviously a difference between us here. Okay.
I think so. But I mean, people can always partner find friends that can handle the mathematics. So collaborative work is always an option. This red mean statistic, I think you can Google it. There's absolutely a source in the paper that will be published in the proceedings. I don't actually have a source here, but I think if you Google it, it will come up with the same of what I've got here. It's an approximation from quite a horrendous equation that I'm not even sure is calculable. But I think it works fairly well. But look at the proceedings for a citation for it, or just Google it.
Yeah, I actually looked. I missed it, I guess. I'll look again, and I'll try Googling.
Googling seems to work better than some of the other search engines. Not that I'm particularly pro Google all the time, but it does have an advantage, I think, at times.
Right.
Very good. Thank you.
Thank you.
Next, let me get Jim Andre up here. Just a moment. All right, Jim, if you are unmuted.
Okay, I think I am.
You are.
Yeah. Hi, Tony.
Hi, Jim.
Just had a quick question for you. Once you've selected your areas, the spots on the stamp that you would like to analyze, use for your color analysis, would it be useful to blend the color within that spot so as to get a uniform color across that spot rather than getting a distribution of RGB values like you showed?
God, that's quite a good question. I'm not sure how you would blend it, but in effect, I've done that by averaging the RGB values. Mm-hmm. There is actually a problem in averaging RGB values in they're not linear. So you actually have to average them using a transformation. And actually right now I forget what it is, but it's basically a sort of logarithmic transformation, and then you back transform it to get a proper average. I'm not sure if you can tell us now how you would blend the color.
Well, the tools I use have a blending function. I mean, they're image manipulation tools
in the
like
software.
Yeah, in the software.
Oh,
it's
okay.
Like or GIMP.
I see, Jim. I've got you. I imagine that the blending does exactly what I do when I average the RGB values. Again, it's in the paper that will be in the proceedings, the method I use, but it isn't in this talk. So they would probably use the same algorithm to blend the color as I've used on the separate RGB values. It's just that doing it my way, I have more control over the algorithm used, whereas the software, you just don't know what's going on. So I think it would be the same.
Okay, thank you.
All right. I've got Mr. Morell asking more questions here. Let me activate him. Go ahead.
Hello again. I'm trying to recall. Oh, yes. My question has to do with the Kate software, the add-on to Excel. Can you show us that plot once again? And perhaps you or Richard could explain what data set the software uses and to interpret the resulting plot.
Yeah, sure. So the Kate add-on to Excel, again, the reference is in the paper, but not in this. Oh, no, the web page is here, actually. So it's World Wide Web at kateexcel.com. So you could even go to that directly. For this plot, it just requires 3 different XYZ. Well, actually, the RGB values in 3 clusters. So it's a very simple plot to do. And then you just link that up, which allows you to do a 3D graphic, which you can rotate really nicely. And these 3D plots are really awkward. So these axes are red is in, I've actually taken the labels off. Red is in one direction, green is in another, and then blue is the third axis. So it just allows you to visually separate out the clusters. So that's quite easy to do. It's just so difficult to display on a piece of paper. And often when you're playing with it, you can rotate it and you get a very good 3D representation in your head of the different clusters. But when you come to plot it, it really doesn't work very well. So, yeah, I hope that. Was there more to the question than?
No, I can see the clusters. There are 3 ovals on the plot, and I understand that each one represents features of the different types of paper that were used, or ink. Now, speaking of which, did you determine what the ink was in the original print? And you mentioned that there was a later printing, and the date is not certain perhaps, but a later printing using aniline as the synthetic dye.
Okay, that's partly for next week's talk. I'm actually giving 2 different talks. So
I can wait. If you want to defer.
I won't go into that in detail. Now, all the stamps were printed at the same time as far as we know. So there was just one batch of printing and one shipping to Newfoundland, and they were all issued, I think on the, what's the date? 17th of September 1939, or whenever they were issued. And then they were issued until they sort of were withdrawn. And I can't remember when they were withdrawn, but I mean, 6 months later or something. So there's just a single printing. So why the aniline stamp? And this is very much the topic for the next presentation. So I'll go into that, but it's all probably from one printing.
Very good.
Yeah, we'll wait till next week.
I'll be in suspense until then. Thank you.
Not just you. We all will.
What about a great cliffhanger? Thank you.
All right. With that, we've been through the questions. Mr. Barwis sends along his congratulations for the great work you've been doing, Tony. Let's take a 15-minute break. We'll reconvene at 1:15, wherever you are. Use this in any way that you choose, and I look forward to having you back here in a few minutes. Thanks.
Yeah, thank you.
Good afternoon again, for those of us on Eastern Time anyway. Now, our next presentation is by Richard Judge, who is pretty well known to those of us who are around Analytical Philately. Richard's a molecular, I can't say that word, spectroscopist by training. He had a short stay at the Ontario Ministry of the Environment as head of the XRF and XRD lab before joining the chemistry department at the U of Wisconsin Parkside. He's now a professor emeritus specializing in the analysis of BNA postage stamp inks of the late 19th and early 20th century stamps. So with that, you can see we're headed into some I cannot say it today. Spectrographic study. Richard, please take it away.
Thanks, Ken. It's a pleasure to be able to present this material. I'll be talking about Prussian blue, and as a pigment, it's pretty ubiquitous in the philatelic world. So perhaps the best way to start off the talk is to talk a little bit about, oh, that's odd. I'm not advancing my slide. Are you seeing my slide right now?
Yes, we are. Oftentimes, the first advance you have to do down at the lower left.
Okay, there we go. Thanks. Okay, the key pigments in this are ultramarine and Prussian blue. These were taken with my cell phone camera right out of the bottle for the ultramarine, and you can see the structure to the pigment. The Prussian blue is almost black here, and indeed it is extremely dark, and it just shows up almost as black here. The modifiers are calcium carbonate, lithopone, and zinc white. These are all intensely white compounds, and they're used to moderate the ultramarine and the Prussian blue. Okay. The spectra we're going to look at are from X-ray, FTIR, and reflectance. And that's the three main ones. The first one we're going to look at here is the XRF spectrum of Prussian blue. And the black trace that you see is on scale to about 100,000 counts. And it represents virtually only iron. That's all you're going to see in that particular compound. If you blow it up considerably, and you go to about a 5,000 counts per second scale, you can start to pick up some trace elements in this particular sample of Prussian blue. It's a commercial sample. You can see some zinc, and what I've indicated here is a ×2. That's a pileup of the photons from the iron at double the frequency, and there's a small escape peak. And there's a tiny titanium peak that you can see to the left of the escape peak. So there's a bit of contamination, but it's almost pure iron as far as the X-ray is concerned. In the next slide, we look at the ultramarine. And on the scale here, it's only 10,000 counts. So it's, in terms of the X-ray, it's almost transparent. There's an artifact of my instrument is that you always see iron and the K alpha line of iron, the K beta line to the right. And then there's another line that's also showing up, which is probably both of them are coming from the components that make up the X-ray spectrometer. A little bit of iron, a little bit of nickel in the hardware that makes up the instrument. So that's always there as sort of a background. And you can really see it here because I've blown up the scale. In terms of what's in ultramarine, it's mostly sodium, aluminum, and silicon, and a little bit of oxygen and sulfur. You pick up the sulfur nicely. You pick up the silicon, aluminum very, very weakly. And that's because the way I've set up my instrument, I throw in an aluminum filter to try and get rid of some of the exciting radiation from the tube, so it doesn't interfere. You also see a background essentially from the oxygen and any other light elements that are in there. In the next slide, okay, you're looking at the FTIR spectrum of Prussian blue, and its contribution or its identification is mostly through the peak at 2077 reciprocal centimeters, which is due to the vibration due to the carbon, nitrogen, or the cyanide group in that particular molecule or structure. I've indicated the structure here. Prussian blue can come into two types as far as we're concerned here. There'll be these insoluble and the soluble. The soluble form has potassium as a counterion, and the insoluble form, its counterion is iron. In both cases, iron is the counterion, but in the case of the soluble one, potassium and iron are both present there. And so in this particular sample that I've got, commercial sample, if you look back at the previous slide, there was no potassium. So we can say that it's the insoluble form of Prussian blue. As an aside, like when we say soluble and insoluble, that's sort of a misnomenclature. The solubility refers to the ability of Prussian blue in the potassium form to form a colloidal solution. And so it looks pretty much like a solution, but it has the property that it scatters light for one thing, and it's non-filterable, but it is not a true solution. Okay, so it's a bad choice of words when you say a solution, or soluble or insoluble. Both forms are extremely insoluble, as it would need be, because you're dealing with a cyanide group, and if it was available to your body, it would not bode well. The ultramarine spectrum the FTIR is totally different. Here there's only one or a couple peaks very low down, around 1,000 reciprocal centimeters, and that's due to the silicon aluminum stretch, and a couple other peaks that appear. One of the characteristics that is unfortunate for ultramarine is that the peak at 1,000 just happens to be right on top of where cellulose absorbs in the paper on the stamps that we'll be looking at. And the cellulose is always there in these engraved stamp because, of course, between the lines that have been engraving, there's some paper showing up. The nice feature here is that in the ultramarine, the peak is very symmetric. There are no shoulders and so on. So you can sort of tell them apart between cellulose and ultramarine by the symmetry to that particular peak. As an aside, I've shown the structure to the left there, and you can see the cage structure due to the silicate. But inside the cage is the compound that gives ultramarine its color. It's sulfur 3, S3, and it represents a molecular transition in that particular molecule that gives it its blue color. As further aside, you look at the formula on the top, I've indicated S4. Apparently, the supplier of this particular sample that I bought indicated that it's S4 instead of S3. And apparently, ultramarine comes in two forms, S3 or S4. I'm not 100% sure where the extra sulfur is coming in. But the reason why it's blue is from S3. Okay. The last one is the reflectance spectra of these two compounds. And the ultramarine is in light blue, shown there. And then the blue is the Prussian blue. And as expected, the Prussian blue is very low in reflectance. It's very darkly colored. And around 450, you get the blue color. Similarly with the ultramarine, although everything is shifted upwards. But what's important here is the shift at around 700 nanometers, where you start to see or move into the near infrared, and the ultramarine just takes off and becomes becomes reflective, as opposed to the Prussian blue, which remains non-reflective in that area. So this is a nice technique for the VSC 6000 to be able to differentiate between the two samples. You don't need an X-ray or FTIR. You just look at the reflectance spectrum and how it behaves in the near infrared. So the three species that I'm going to look at here are the Scott 233 and 233A. It's a Prussian blue pigment, and that is a true error. That is the Bureau of Engraving and Printing actually made an error. They used the wrong ink, and they produced a variety which is indeed an error. The next one we'll look at is the Newfoundland 124. That's the trail, that's spelt wrong, the trail of the caribou. All stamps contain Prussian blue. This is an example where there is no error. And then the final one is United Nations C3 and C3A, and that's the Prussian blue missing error, which I'll go into in a moment. So again, to recap, you have a stamp where it's a true error, a stamp where there's no error, and a stamp where it's miscategorized as being an error, but it's missing the actual pigment. So I'm going to start off with the Colombian issue. And as for historical reference, I'm going to reference the really nice work of Thomas Lara, who published this in the Collectors Club Philatelist. And it was the definitive study to show that the Prussian blue is indeed an error due to the manufacturer or the printer. So to summarize his results, what I've got here is the Prussian blue is in red. So that's the Prussian blue error. The Prussian blue 1 cent is the one in dark blue. And then the turquoise, the natural color for the 4 cent, the non-error, is in turquoise. And you can see that if you look at just the iron peak, the Prussian blue and the blue and the red are on top of each other, whereas the turquoise is that background of iron. So that is your distinguishing feature for as far as the X-ray is concerned. The other elements are all there present, except for maybe a little bit difference in the intensities of the lines. But they're all, the formulation for the other elements that are present are virtually the same. The major difference, again, is that it's missing Prussian blue. And that's confirmed in the Colombians on the FTIR, where you can see very definitively that the Prussian blue 1 cent, dark blue, has a nice peak at roughly 2100 reciprocal centimeters, the cyanide stretching, and the Prussian blue error in the red is also there quite definitively, and then the turquoise or the Prussian blue normal, the 4 cent normal, it's not there, it's absent. The other elements are pretty much the same: calcium carbonate, barium sulfate, cellulose. So that's sort of, as a final nail in the coffin, is the reflectance spectra of these three species. Again, the Prussian blue error and the Prussian blue 1 cent have identical or nearly identical reflectance spectra, and the fluorescent normal tails off very sharply into the near infrared. So that, in summary, is the work that Tom did on that particular sample. And as I said earlier, it's sort of a definitive and a casebook example of how to find or look for Prussian blue. So having said that, I was asked by two friends, John Walsh from the Newfoundland study group and Garfield Porch from the Green Foundation, if I would look at their 15-cent Newfoundland Prussian blue air, which causes a fair amount of discussion when it comes up for analysis or for an opinion at the Green Foundation. So they very nicely sent me their copy, which was the Green Foundation copy of the standard Prussian blue air. And then John Walsh arranged for me to get the APS or the Apex standard, along with about 4 or 5 other regular Prussian blue samples. And this is what the next part of the talk will be about, is that looking at these particular spectra. But since we're a bunch of philatelists, and we've often been accused when we talk about spectra all the time of not showing enough stamps, I decided to show you a very nice series of what this looks like for that complete series of the Trail of the Caribou. It was issued right after the war, and it commemorates the contribution by the Newfoundland regiments to World War I effort in aiding Great Britain at various battles. And each stamp represents a particular battle or a service, part of the service that contributed to it. The 15-cent is the one we're going to look at, and it's sort of is the strongest color of all, at least my opinion. It really does stand out. So, having said that, what I've done here is to show you a composition of the stamps that I obtained after I did the analysis for the Green Foundation and for John Walsh, is that I wanted to use my own stamps to augment the relatively few standards that I was using. And then I also went out and bought a RPSL certified copy to compare with what I had. And so if you look at these, you can see there's enormous variation in, just by eye, in the darkness and the shading of these particular stamps. And a lot depends on how thick the ink covering is on the stamps. So this made for an interesting collage, if you like, of showing the different properties of these stamps. Okay, so what I'm going to show here is my results for the RPSL certified copy and the roughly 24 other stamps that I used as a standard. And so you can see that the dark green is sort of a blurred out because, sorry, the other way around. The light blue is sort of blurred out because it's a multiple averaging of all the 24 other standards that I used as non-certified. And the certified copy is in dark green. And as you can see, the major difference between the certified copy, looking at the K beta line, which is the iron written on it, it's a little bit less intense than the others on average, but all the other elements are present there as expected. So there's no difference between this certified copy in terms of the X-ray spectra and my 24 other averaged out samples. I found the same result with the two copies from the Green Foundation and APS and the limited number that I worked with originally. The next one is the FTIR. So again, looking at the two standard instruments for this particular compound, you can see again that the Prussian blue in the certified copy in dark green is virtually the same as the others. Okay, it's again slightly less than the others. and it has all the other compounds that are present in the uncertified copy. So again, it's telling you that there's no difference between this and the other sample. And then the final, I guess you want nail in the coffin, is that the reflectance spectra shows, it's in the middle of everything else. So why do people insist on saying that Prussian blue has a particular shade to it? In other words, why is there so-called Prussian blue error to this particular stamp when I can't show any reason for it? And it all has to do with the physics of, or the physics of the Prussian blue pigment. It turns out that multiple synthetic methods of production for Prussian blue result in different counter ions, which I mentioned earlier, and that counter ion can give a small effect on the hue. Okay? But more importantly, the different production methods give rise to different particle sizes, and diffuse reflectance from different particle sizes of the same compound will have different perceived hues. So we can have exactly the same compound, and depending on how finely ground it was mixed when it was added to the pigments or into the other components that make up the pigments or should make up the ink, you're going to get slightly different shades according to your eye. Which then begs the question, philatelists love looking at different shades. And certainly I do enjoy doing that. Once you get a collection of stamps, you tend to put them in different piles based on your perceived color or shade differences. So how can this be handled? And my opinion is the following, and I think the Green Foundation has got a really nice solution to this problem. They have their particular copy of what they call Prussian blue, and they can compare it to others. What Garfield did was to run the VSC 6000, get the reflectance spectrum, and match that reflectance spectrum to a standard Pantone color chip, which is available commercially. And they essentially said, when you submit a copy to us, we're going to compare it to this Pantone chip in our standard. And if it's within a certain statistical range for variability, it will be said to be Prussian blue. The nice advantage of this technique is that if you've got other expertising agencies that are willing to, who have a VSC 6000, use the same kind of standard for their white background, and using the same commercially available Pantone chip, you should be able to have uniform agreement about what Prussian blue is. So this perhaps may set a standard for being able to do color analysis. So that's my opinion, and I'll leave it like that and move on to the next section, which is the United Nations C1 to C4. It was their first issue of stamps, and this is the first issue for the airmail edition. And what we're going to look at is the 15-cent copy over here. And if you look at the Scott catalog, and if you look at Merkel, apparently both of them have a Prussian blue error. The error is about maybe $30. The standard stamp is about a minimum Scott 25 cents. So there's a bit of a premium on having the error. And when I came across this particular listing, when I was looking for getting some stamps sorted for a friend and wanted to know if it was of any value, I came across the listing that said Prussian blue. And of course, I just finished the Newfoundland issue. So I looked at it and said, well, maybe it'd be fun to purchase a Prussian blue standard and look at it and compare it to the normal stamp, which is what I did. I went out and purchased this very nice block, which was certified by the Philatelic Foundation as being Prussian blue. And later on, I bought a second one on eBay from certified by Gaines, and I resent it for certification again by Apex in 2020. So I have 2 copies of the certified Prussian blue air, and when I ran the spectra, you can see that the Prussian blue air is in, the block is outlined in yellow, and the signal is in blue, and I sort of rearranged things a bit, but the reds are all the standards, regular compounds. And as you can see that in all cases, the standards, or if you like, the non-errors, all have iron, Prussian blue. The spectra are remarkably similar in all sets. And so my first conclusion is it's just like the case with the Newfoundland issue, is that all stamps are Prussian blue. But I wasn't satisfied with just having maybe only 3 or 4, or maybe at that point, maybe a dozen copies of the standard. I went out and bought, because it's inexpensive, I bought a lot more samples of regular samples on eBay and various places. And so over the course of time, I amassed about 130 samples of the stamp. But around the 34th purchase, I came across a stamp, and when I ran it in the X-ray, I came across what turns out to be the Prussian blue missing error, in that it had no Prussian blue. So this really sparked my interest. So I went out and bought some more. And over time, after analyzing all the spectra and categorizing them, I found that I could categorize them into a low Prussian blue, which is on the left, called the earlier printing, and a higher Prussian blue content, later printing, and the error is smack in the middle. So it turns out that the error is fairly common. It turns out to be about 9% of the samples I've got. So I've got about 5 or 6 of these characters in my 130. But here's the proof that the Prussian blue is missing, is that if you combine all those normal samples as dark blue or turquoise, and then the error, Prussian blue error missing, as red, you can see that it really does stand out by itself. Okay? So there's very little doubt that there's no Prussian blue in that particular error sample. Similarly with the FTIR, you've got Prussian blue missing as that red line, sort of a flat baseline, the lighter blue being the low Prussian blue, and the higher dark blue as being the higher level. Again, it contains calcium carbonate, and the other element is ultramarine, as we're going to see in a moment. The final proof, again, is in the reflectance spectra, where you can see that the light blue, turquoise, lower Prussian blue, all sort of go off into the infrared as normal for Prussian blue, whereas the Prussian blue missing, again, goes tailing off quite higher into the near infrared. So that is, again, an inexpensive way for philatelic agencies to identify the Prussian blue missing error. Simply look at the reflectance spectrum. Now, the final experiment was to look at the emission from the white paper. Now, it turns out, if we go back a little bit, maybe I'll show you the stamp. If you look at the bird right above the UN symbol, you can see that it's completely white. And that is no pigment in that particular area, which was a real blessing. So I could look at the paper without having to worry about the gum. Okay? And so the experiment is quite simple. I got hold of a UV diode, a 370 diode, hooked it up to a source, a battery essentially, and piped it into a fiber optic cable, which I've tried to show here. So the 370 diode ultraviolet light falls on the stamp paper. It then fluoresces from the pigment, or not the pigment, but the whitener that's in the stamp paper, and it fluoresces around 450 nanometers, if I remember correctly. You then filter out the 370 diode frequency and pass that into a spectrometer. And here's what you get. You can see that the light blue down here, the turquoise, those were the low Prussian blue pigment, low concentration. They have virtually no fluorescence at around 435 nanometers. Okay? The darker blue, okay, and the Prussian blue missing air all have fluorescence noticeably above the background, and they then characterize the paper fluorescence into two groups. At least that's what I've done, into non-fluorescent and fluorescent. Now, earlier philatelic studies had shown that they categorized the fluorescence as non-fluorescent for the first two printings, as you'll see in a moment, and then the third and subsequent printings, they were said to be various levels of fluorescence, some high, some low, some medium. Rather than going into trying to quantitate that, I just said either it fluoresces or it doesn't. So having said that, I looked at the various dated samples that I had, December 3rd, 51, 54. And if you look at the printing dates, okay, 51 to 54 is printing numbers 1 and 2. And then on the third printing of March 1956, they went into third and subsequent printings. And if you look at the limited number of first day covers that I've got here, you can see that 1 and 2 correspond to printings 1 and 2. And then the subsequent ones, 3 and 4, correspond to the later printings. And again, they have that very high fluorescence at 435 nanometers. And then there's the air, Prussian blue air, which has fluorescence at, again, 430 nanometers. So the conclusion then is that the Prussian blue missing air had to be in the fluorescent era. And if you look at the fluorescent era, it starts at third printing and moves on. Now, the nice thing about luckily finding this particular cover is that the receiving date is October 12th, 1956. Okay, just about between the third and fourth printing. So this particular cover was produced or mailed in the between the third and fourth printing era, but it contains a stamp that has fluorescence indicating that it started at the third level, third printing sequence. So conclusively, using about 4 different spectroscopies, you can show that the Prussian blue air occurred during the third printing. Now, this is quite contrary to the established literature, which indicated that they thought it was in the 5th printing from, I guess, anecdotal evidence. And one of the things that was mentioned in that particular choice of the 5th printing is that the pigment was mercuric sulfide as being added to the stamp to give it its peculiar color. This, the Prussian blue air color. Well, I find no evidence for mercury anywhere in the samples that I looked at. So I'm pretty sure that that story is probably wrong, and that the actual error occurred in the third printing. Now, to finish up, we can look at a way of synthesizing the spectrum, which was kind of nice because there's very little paper showing through in these stamps. The ink is very, very heavily concentrated. And so what you can do is take the see, the black spectrum is an observed spectrum, okay, of just a regular Prussian blue sample. And you can synthesize a spectrum by using Prussian blue, calcium carbonate, ultramarine, cellulose, and barium sulfate at various absorbances in the FTIR spectrum. And you can see you can make a pretty nice match to what is observed and what is calculated in the synthesized spectrum. And then finally, you can look at if you start blowing things up enormously, you can end up with, if you match the barium level, this is the L lines of barium, and if you match up in the regular sample, the barium level, to this Prussian blue missing level, then you can actually see that the barium is in here, as in these black lines around chromium. But chromium is definitely there because there's a slight shift and you get this little peak shifted over what barium is normally there. So it's showing that there's a small amount of chromium in the Prussian blue missing area. Now, along with that, there's also a small amount of lead, which shows up. It's absent in the regular sample, but the Prussian blue area is missing lead. Prussian blue area has lead in it. So, final conclusion, or at least speculation, is that they added lead chromate, which is yellow, to the sample in order to doctor it. And so, because ultramarine is so light in color, again, I'm sort of speculating, is that they added a lot of carbon black to get it darker. They added less than normal amounts of barium sulfate or lithopone to lighten it up. And they added a little bit of lead chromate to throw in enough sort of yellow to try and get a good match to what Prussian blue looks like. And so with that, I'd like to end up and say thank you for listening to my talk, and entertain any questions.
Thanks, Richard. The first one up is from Yanni Hofmeyr. He should be able to just unmute and ask. Yep.
Hi, Richard. How things? I want to make sure that I understood. I mean, first of all, I find this, I love this stuff. So thank you for doing this. I want to make sure that I understand the conclusions, though, from the point of view of a philatelist who wants to know what color their stamp should be called. Because it seemed to me from the second, I mean, you start off by saying, there are pigments that are called Prussian blue and there are pigments called ultramarine, and these are their characteristics. When you subject them to these different analyses, there's a Prussian blue error in the Newfoundland stamp. And it's catalogued and it's recognized and it's classified. But then your analysis shows that the examples that you've got sit right in the middle of what's generated when you do an analysis across a whole lot of stamps. So I guess my question is, does that mean that the constituents don't matter when it comes to what we call a stamp, what shade we call a stamp?
Exactly. The problem is that there's the confusion between the pigment and what I guess printers or graphic artists would call the color.
Yeah.
So when they say Prussian blue color, they don't necessarily mean that Prussian blue was actually used in the making of that stamp.
Yeah.
Or when they say ultramarine, they don't necessarily mean that it was ultramarine pigment that was used. So there's this confusion between the pigment name and what the catalogs call various colors.
Yeah. So again, pressing a little harder, the importance of the sort of what are the constituents analysis. The importance of that kind of analysis for philately is that it helps us to distinguish whether something may be fake or not. For instance, because a particular compound didn't exist at a particular time, and then a cancellation was faked. But it doesn't necessarily answer the question about what color the stamp is. By identifying what inks were used, you're not going to answer the question, what's the shade of the stamp? But in the third one, you do show that something is missing in what is recognized to be an error. And my summary would be, that's not a problem, because it is a visually identifiable difference. Would that be correct?
Yes. I guess maybe if you could just explain your question, rephrase it a little bit.
So there seem to me to be two questions for collectors. The one is it real or not? Is it fake or is it real?
Right.
And there, the sort of analysis that was done in the first paper answers that question. The second question is, what shade is my stamp? And what you really showed with your second example, which I love, is that that can't be, the ink doesn't matter. The constituents don't matter when it comes to answering that question.
Agreed. And again, even the the catalog makers don't agree on the shade name.
Yeah.
So
I'm convinced, especially from Anthony's presentation, that we should just throw the catalogs in the rubbish bin. But that's a separate conversation. Thanks, Ken.
All right. Yeah, we can. I don't think that's an IAP issue, but certainly worth a discussion. All right, Louis Morrell, you are up next, and I think all you have to do is unmute.
Done. Richard, I think you mentioned earlier that the UN stamps were all printed by the Bureau of Engraving and Printing in Washington.
No, I'm sorry if I gave that impression. The Colombian issue was Bureau of Engraving and Printing. The UN stamps were printed by, I think it's De La Rue.
Okay. So my question has to do with the supply of ink. During that 9 to 10 year period in the 50s, did the Prussian blue come from a single supply house? Was it American, British, German? And could the quality there have changed, which would compound the issue of uniformly dispersing the ink in the process onto the paper? Could they have had quality control issues themselves, the suppliers?
My experience with contemporary stamps from about 1940 on is that the X-ray spectra are remarkably constant over the number of stamps. And so my guess is that the Prussian blue, they may have had different sources. And again, that would explain small variations in shades. But again, even within a production run, as you probably got near the end of the tail of the run, and the ink was getting thicker and the particle sizes were getting a little bit larger, it's being spread out properly, the shades are going to start to change simply because the particle sizes are changing as the production proceeds.
Okay. And that would account for some variability.
Yes. I mean, the nature of Prussian blue is that given on the day that it is ground up and the day that you're not necessarily looking at it, but depending on, again, I go back to the particle sizes, depending on the distribution of particle sizes that you're getting in a particular batch, you're going to get different shades.
I understand that, yes.
The other problem with Prussian blue, which doesn't really affect us much, but it will fade in sunlight. But again, it regenerates later on.
Really?
So as far as we're concerned, presumably the longer you look at the Prussian blue under a light, the color is going to change on you, the shade's going to change.
Okay. Okay, that makes sense. Very interesting. Thank you.
Thank you. Now, another question has come in from Paul Davey. Paul?
Right, yeah, just a quick question. If you say Prussian blue error to a GV collector, they automatically think of the Tuck Me Hate Me Jubilee of 1935, where there are a couple of sheets in what's known as Prussian blue. Have you ever looked at one of these?
I'd love to, but the problem is I can't afford the stamp. So I suspect that the RPSL did an analysis on the X-ray and found this, that is significantly different, that it is indeed an error. But I have often thought about what tests have been done on that particular stamp.
Okay, be interested to talk to the RPSL expert committee and see what they've done.
Yeah.
All right. I have no more questions in the queue.
Okay.
It is 1:00 on the nose. Our next presentation is scheduled to be at 1:15. It will be Russ Sampson.
Can I, I'm sorry, this is Susan. Can I ask a question?
Of course.
I'm finding that as a panelist, I can't actually type into the Q&A. I don't know why that is. Thank you, Richard. Can you explain what you mean by Prussian blue regenerates? It fades, but then it regenerates.
Yeah, again, it's what I've read in the literature. I suspect it's an equilibrium problem. Okay, so in the charge transfer, when it transfers the electron from one species of iron to the other, if you build up enough light intensity, you'll shift the equilibrium. It's the Le Chatelier's principle. You just shift the equilibrium to the lighter shade. And then as you return back to ambient light, it'll just shift right back again. So it's stress on an equilibrium system. I don't know if that answers your question or not.
Thomas Lamb, one of our presenters, offered that it's oxidation dependent, Fe2 and Fe3.
Right. It's a transfer. It's a charge transfer where electron goes from iron 2 to iron 3 or back and forth. But to answer Susan's question, there's a principle. If you have an equilibrium between these two species, the number of each one, with or without iron, with or without electron, if you stress the system and you force it in one direction by adding, by essentially pushing more light into one, you'll push the electrons into one species. And then if you remove the stress, it'll return back to its equilibrium position.
Okay. Can I ask an additional question?
Sure.
You had mentioned the process of engraving a couple of times. What is it that we should be thinking about with engraved stamps in relation to studying these questions in terms of perhaps the status of the plate over time, the thickness of the inking? What are some of the things that we should be considering as we ask all of these questions in specific reference to engraved stamps?
Yeah. The engraved stamps present real problems in terms of your perceived shade when you look at a stamp. And Russ Sampson's going to be talking about this next time. And what he's going to, don't remember the exact phraseology here, but he's finding that the background makes a hell of a difference in your perceived shade perception. So in terms of how thick the ink is put on, it's going to make a difference in what you perceive as being the shade. No doubt about it.
Yeah. We've, for the inverted Jenny and the Jenny surrogates, that we used, one of the things that came up in the literature from the World War I period, a response to people that were concerned about the shifting, what they perceived as color differences during World War I period, was the age of the plates. That was one of the official responses. Whether that was accurate or not, I don't know, but that was an official response, that they were short steel, for example, and using plates longer than they would like to.
Mm-hmm.
And that was one of the justifications, basically, for the public perceptions changing.
Yeah. Again, this goes back to the thickness of the ink.
Right.
And our eyes are not very good at deciding on shades. At least mine aren't. And you can get fooled very easily by just the same pigment, the same shade, but if it's thicker, it looks darker.
Right. Yeah. Thank you.
Okay.
Thanks, Richard. As usual, very, very interesting. We have, like I said, we have our next presentation scheduled for 1:15. Let's take a 10-minute break, and Russ, you will be up. Thanks to everybody, and we'll talk to you in 10 minutes. All right, it's 1:15, and I will first offer a short apology that I was turning my video on and off without any trouble, and starting about an hour ago, it wouldn't let me turn on anymore. So I'll have to solve that between now and next week. Our next speaker is Russ Sampson. He's a retired professor of physical sciences. His professional research interests included astronomy, atmospheric optics, photogrammetry, and science education and outreach. His philatelic research interests include Canadian perfins and, more recently, colorimetric analysis of intaglio stamps. And with that, Russ, you're on.
Thank you very much, Ken. Can you hear me?
Yes, sir.
All right. Yes, as my little bio suggests, this is my first foray into colorimetrics, and congratulations to everybody that has preceded me on wonderful presentations. And I have learned a lot. And as you'll find out, there'll be my first foray into this. I'm in the beginning and the fun end of the learning curve, and so there will be more to follow. Okay, so let's get started with an outline of my presentation. The stamps that I'll be doing, this is a colorimetric analysis of a relatively common Canadian stamp, the Scott 223, compared to the Unitrade 223I. They're both just about as common, about 50% of the deep rose shade. That's what I'll be looking at. Can be found at least if you take the catalog value as a guide versus the carmine. I'm using a little bit of crowdsourcing. I'll explain my crowdsourcing experiment to come up with the initial question. I'm going to then put together a causal hypothesis, what I believe is the cause of these shade differences, and then talk about experimental controls for uncertainty, for the RGB uncertainty. And it's very important to understand this is relative RGB, not like what Tony was talking about, absolute RGB, to try and determine what exactly the color is. I'm comparing one stamp to another, and so in the same scan. There it is there, relative RGB. And the most important result of this research is the paper values of the RGB, and I'll go into that in great detail, versus the ink values, and I'll discuss that. Then I'll come up with a color. I should have put theory in quotation marks there. Now that there's some data involved, it turns from a hypothesis into a theory. And then I'll discuss new directions in research, stuff that I'm doing actually in the last couple of weeks regarding this this particular stamp and my hypotheses. Okay, so let's take a look at the crowd sourcing experiment. Philatelist came to me one day and said, I cannot tell the difference between these two shades. And since we're perfect collectors, we collect almost exclusively used stamps. And so there's the whole problem of staining and age and what have you. And so I put together these nine, and because they're of equal value, we expect there should be at least one of the shade difference or shade varieties in this. And then I invited 4 philatelist friends to, I sent them JPEG files, the exact file that you're looking at here. And I told them to independently determine which one was darkest and which one was lightest. And they almost unanimously concluded that the third one, the top right one, was the darkest shade, and the bottom left one was the lightest shade. And from that, I came up with a possible causal hypothesis. And let's just go back there. You can see, look at the shade of the paper here, and you don't have to have photogrammetric eyes to be able to tell there is definite shade differences in the paper. 2 things. One, the perceptual, and Richard alluded to this. Thank you for your nice introduction to my presentation, Richard. Alluded to this. There is going to be a perceptual component to our deciding which shade we are seeing in our stamps. And the one perceptual effect that I want to talk about is called the Bezold effect. There he is right there, Johann Friedrich Wilhelm von Bezold. He was mostly a meteorologist, much like partly what I used to do. And he was also interested in the visual perception of color. And here is the Bezold effect as it appears in most textbooks. The red lines are constant color. There is no shade difference from left to right. However, the Bezold effect says that the perceived shade of the color is a function of the color that it is adjacent to. And so in this case, it's black. The red stripes on the right appear a darker shade of red than the red stripes on the left. In intaglio stamps, of course, the lines are much thinner, and the shade differences that we're dealing with in paper are much more subtle than black and white. And so here I put a 15% gray and a white background. The red remains the same color value, and what I've done is made them much thinner, and then I'm going to make them even smaller to make it, again, appear more like an intaglio stamp. And son of a gun, you can definitely see the shade difference there, even though the red is the same color. And then the next part of the hypothesis involved ink transparency or ink opacity, depending on which way you want to look at it. Is there a component of light that actually passes through the ink and then is subsequently reflected off of the underlying paper? And that, of course, would change the perceived shade of the ink as well. And here, again, I've put a white on the left and 15% on the right. And I'm going to now bring in the red that has, I can't remember what transparency. Yes, a 0.25 transparency value. So a quarter of the light is being transmitted from the background to your eyes. And yes, we can see a definite shade difference from left to right there in the red. So now I came up with an empirical experiment to test this on the 9 samples that you saw in the first slide, or I'm sorry, the second slide, and tried to control for some measurement uncertainties. And now after Tony's presentation, you'll find out there are other uncertainties that have not been taken into account that I will do in the future. First of all, TIFF versus JPEG. TIFF is an uncompressed or relatively uncompressed file format, while JPEG is. Here are 2 identical specimens scanned in a TIFF format and a JPEG format. In the blue screen, you may have to turn up the brightness of your screen to see this, but each individual pixel has its own color value. You can see them there, while in the JPEG, they've grouped them, which saves on file space. And so some of the pixels are grouped together and averaged. And so is there some error? And I sent these files JPEG because I didn't want to send these massive TIFF files through the internet to my colleagues. I wanted to keep them on my friendly side. And so I did an experiment where I tested the variability of the exact same spot on each stamp. One was TIFF, one was JPEG, 8 different measurements, and you can see the uncertainty is 0.69%, plus or minus 0.69%. And in the same specimens, I measured the variability in the intensity of the ink and the paper, and you can see that the the variability is significantly higher than the variability due to the TIFF format, or I'm sorry, the JPEG format. And so I figured that this was relatively insignificant uncertainty, although I will correct for it with future research. And then I wondered whether or not the light source in the scanner that I used, which was an old 550, and so these have these unwanted, as Tony expressed in his wonderful presentation, these unwanted image enhancement algorithms in it that are hard to turn off. And so what I did is I wanted to know whether or not the LED, which is the light source of the scanner, how consistent that light source was. And so what I did was I did a scan of the document mat, which comes with the machine. It's white and very uniform, and I cleaned it. And there are those little red dots. I measured, I think it was a 7-inch by 4-inch area, 10 dots across and 4 dots down, 4 measurement points down, and got these values here on my screen. I can't see that last one there. Let me move this thing. Yeah, so on the x-axis, plus or minus 0.45%, and the y-axis, plus or minus 0.82. Well, you can read it there. And again, significantly less than the variability of the ink and the paper on these samples. Okay, so now, why is it? There we go. Okay, the measurements, each one of and again, Tony and Richard talked about this, is you have to, especially Tony, have to be very consistent with where you measure it on the stamp, fine lines and thicker lines and things like that. And so I measured the ink in the center of these yellow circles here, and the paper in the blue circles, and I measured in 3 different locations inside those ink or paper areas. And because they're used stamps, if there was a cancellation over top of that I couldn't avoid, then I went down to either above the 10s or here in the Canada section where the ink is thickest. And so here's the evidence. We can see along the x-axis here, that is the sum. Again, this is relative colorimetrics, and so I wasn't worried about what exactly color I'm dealing with. I just wanted to know how bright they were and how dark they were. So I summed the RGB, took the average of those sums, and then plotted them with their sample standard deviation error bars. And so the ink is along the x-axis and the paper is along the y-axis. And then using the color picker tool of PowerPoint, I then assembled these gradated chips, color chips, to show the darkest and the brightest of the ink and the paper. The most important thing here is that the majority, actually all of us, agreed that the number 3 sample was the darkest, and there it is. It is both the darkest ink, but most importantly, it is the darkest paper. And then number 7 was considered the brightest. It does not have the brightest ink. Number 4 has the brightest ink, and yet it has the brightest paper. And so nobody picked number 4, which is this one here that has the brightest ink. And so this suggests, I got a question mark there, this suggests that maybe the Bezold effect was dominant in this particular situation. And so here, just as a visual, here's the number 3. I've flipped it so that we're comparing apples and apples. And the most prominent section here is the sky, where the intaglio lines are nice and are relatively uniform, and we can see a definite shade difference. And again, you can really see the paper difference here. And here's number 4. I should have flipped this one too. I didn't. But yes, you can see the, again, paper difference, very distinctive, and the shade difference as well. And so this really, and just to drive home the results here, I've put the heavily inked sections above the P on the left and right side of and this is sample 3, sample 4, the darkest ink and the lightest ink. And yes, you may have to turn up the brightness of your computer monitor, but there is the difference there. And you can also see, just by looking at the ink-free areas, or relatively ink-free areas in the lettering, that the paper is brighter on the right. So, color theory and computer modeling. Now that I've got some data, we can do the Bezold effect with the data. Here, the horizontal lines, thin horizontal lines, are the mean, or I'll call it the median color of the ink. Again, using the color picker tool in PowerPoint, and the backgrounds, instead of white and black, are the brightest paper color and the darkest paper color. And once again, we see a very distinctive Bezold effect. And I'll just shrink it down just to drive it home. Now, ink transparency, what does the data show with that? And this is quite, I found quite fascinating. I have a little stand that I can mount stamps in and then backlight them. And so now we don't see reflected light, we see transmitted light through the stamp. And you don't have to do the RGB at all to notice that this ink is not opaque. It is letting a considerable amount of light through. And again, I can't read it, but at least I think I can remember it. Its transparency is 0.46. So about half of the light is going through the stamp, is being transmitted through the stamp. And so here, we're going to do that same little demonstration with the brightest paper and the darkest paper. And I'm bringing in a Carmine that I took off of, I think it was Chart Pack. This is Carmine. There's the RGB values there. And I've turned the transparency, I've cut it in half from the measured transparency of the ink because the light from, if you're looking at the other side of the stamp, the light goes through the stamp, reflects off of the paper, and then comes back. And so essentially the optical path of the light is now doubled, and so the transparency will be half of that. Nonetheless, we see a very, and again, you might have to turn up your computer screen brightness, but there it is, a nice distinctive shade difference. Same ink though. So the conclusion from this paper is that it's paper. Now, of course, the ink may have something to do with it. It may be a minor component of the shade difference, but from these results, it appears as though a significant contribution to the shade of the stamp, the perceived shade of the stamp, comes from the paper, both from this transparency and from the Bezold effect. Now, on to current work, and this is really exciting. I've been just doing this in the last few days. What is it about the paper? So I did a backlit experiment with the brightest ink sample, and again, and the darkest ink sample, sample 4, which again, nobody picked, but it has the brightest ink according to the RGB values. And the sample 3, which has the darkest ink. And again, you don't need to do the digital measurements here to see more light is being passed through the paper of the bright ink sample than the dark ink sample. And you can even see that the ink, if you go from this section here to that section there, the ink is darker. So what does this mean? Could it be that the paper is thinner? And so it have a shorter optical path, would let more light through. And so I got out my brand new micrometer, wonderful Christmas present to myself. And I measured the ink-free areas. This took a little bit of jiggery pokery with the stamps. Good thing they're not worth a lot. And measured them. Sample 4, which had the brightest ink in RGB. The paper and the N number indicates the number of measurements that I made. So I take the average and the sample standard deviation, which is the plus or minus. The thickness of the paper for sample 4, 83 point, well, you can read it. And the sample 3, the darkest ink, thicker paper by about 15%. So what does this all mean? Here is a little conceptual graphic model on how I believe, and I'm still formulating this, how this works. This is a sort of schematic cross-section of the stamp as it sits on a surface. So there's the ink on the surface of the stamp. There's the paper, and there's the whatever it's sitting on, a piece of paper or the document mat of the scanner. Now, the incoming light we're going to assume is 100% white light, and the first thing that's going to happen is that there's going to be a reflected component that will be colored, the first scattering. However, as I've just shown, there is a high degree of transparency. About half of the light will go through the ink into the paper, and as it traverses the paper, it will scatter off of, and that's what the little arrows are for, it will scatter off of the fibers, starting from the top and going all the way to the bottom, and then it will reflect off of the surface that is behind it. Again, whether that's your mount or the mat of the scanner, and then it will pass through the ink again, and you will have this secondary component that will emerge out of the stamp. Make the paper thinner, and we know what's going to happen is that the same thing for the first order. We have less attenuation of the light as it passes through the paper. And then again, it reflects off of whatever surface you've got underneath it. And again, if these are mint, we have to consider gum. Lord knows we have to consider gum. And then when it emerges, because it's thinner, less attenuation. If the two papers are made of the same kind of fibers or the same kind of compositions as Richard was talking about, then that will change things too. And it will be a combination of these two that will give us the perceived shade. And there's our stamp collector, a nice hat, looking at these, seeing that the stamps have different shades. Now, if this is true, there's a simple experiment, and Tony was actually doing this in his talk. There's a simple experiment you could do, and that is to change the color of the mat that you put your stamp on from, and the most obvious thing would be to change it to black. And this is what would happen, is the shade would change. So that's what I did. I put a sample of the stamp. I think this is the one that has the brightest, was deemed the brightest. I put it under, there it is, white on the left and black on the right. And right there, you can see the shade difference in the sky right in front of the Mounties' face. It's right in front of his face. That's how obvious it is. And the part above the P, if we just magnify that again, we can see that the right-hand side is darker, the left-hand side is lighter. And here are the numbers. Oh, the control panel is covering them. You can read them. You can see that it is significantly brighter on the left. And I measured all the dark areas here. I think it was 8. I can't remember what is my N number in there. 8. So there's 8 measurements in the white area, this area here, and 8 measurements in the along here, all in the heavily inked areas up in this area. I should have put circles where I did the measurements. Oh, and now it won't do this. There we go. And a presentation in this institution can't be complete without one of these. Richard is helping me with doing some induced fluorescent to see if there is any elemental or molecular differences in the inks. And this is there's the specifics of the instrument. These are all the samples, only the paper though, and samples with paper and ink. And so this is the ink here, and the conclusion. Oh, and then we do, I won't go into the details. I am still trying to decipher these results, but here's the XRF results of, again, all the samples. And the basic result that we seem to come up with is we cannot find any obvious any obvious elemental difference or reflectant difference in the inks. So that lends some support to the whole idea of it being paper. The next level, and again, thank you, Richard, for providing these. I'll give them back to you eventually. There's a promise. Is here are the mint samples, of course, age and cancellation and mishandling and all the stuff that go with used samples of stamp can affect the shade. And so we're going to do this whole thing much more carefully with mint stamps. And I thought I would, how much time have I got here? I've got time. I thought I would give the delegates a little bit of fun. And I'm not going to tell you which one I think is the darkest and which one I think is the lightest. I'm going to let you the great mass, unwashed masses. We're going to do some crowdsourcing here. Tell me which one is the darkest and which one. Just write it down. Don't tell me. We got other presenters after this. And just email me what you think is the brightest and what you think is the darkest.
Russ, you still got quite a bit of time, so.
Okay. So I'll shut up for a sec.
I take that back. We scheduled Yanni for 1:45. So the email.
Okay, well, I'm almost done. Okay, so there you go. If you want me to, I'll send you this file, and you can do it at home, in the comfort of your own home. And I'm going to bias you here, I guess. Here are the two that I figured are the brightest and the darkest. And I kind of reversed them here. 12 on the left and 10 on the right. I've not completed the RGB values, and I've just bought a brand new scanner, the 850 Deluxe with the racing stripes. It's a beautiful scanner. And so I'm going to follow Tony's advice and make sure that it's all the options are turned off. And so here we can see, again, if we use the sky area as an example, we can definitely see the shade difference there. But look at the difference in the shade of the paper. Pretty obvious. And I've cut sections off of the left and right-hand side there. And I'm sorry, I had to put this in. I couldn't help myself with apologies to Disney, and I'm sure I will have their lawyers knocking on my door any minute now. I'm sure to be sued. Okay, so other stamps. Sampson Shu of the Royal Philatelic Society of Canada gave a wonderful presentation on stamp shades. It's online. You should look at it. And he was generous enough to give me this scan of the Hong Kong King George VI, 50 cent, and the three different shades. And the one on the left, the red purple, the Yang 142 is pre-war, and the 163 and 163A are post-war. But here, take a look at this. Take a look at the difference in the shade of the paper. And here's down using the color picker tool. I've shown the color of the ink from a heavily inked area and the shade of the paper. And so it appears this is not confined, this phenomenon is not confined to the Canadian RCMP stamp, the 223. It may be something of more common occurrence. So this may contribute, the whole idea of paper being significant may contribute to what I like to refer to as intaglio color theory. We've heard a lot about ink and its incipient color, the color before it's put onto the stamp. And we've had questions about thickness on the stamp and engraved line depth and plate wear, opacity of the ink. And then advanced optics like Rayleigh scattering and edge effects that could influence the color of the ink. And then, of course, color degradation. And as Richard said, coming back. And I hope this at least strongly suggests that paper may have a large degree, large role to play as well. Its incipient color, its albedo, its reflectivity, how much light it reflects, its thickness, as I've demonstrated, and then, of course, age and degradation. And then finally, which may be the most complicated and most, I think, interesting component of figuring out a stamp's shade, and that is the eye brain and its complications and weirdnesses, as I've shown with the Bezold effect. And so all three of these would combine in whatever proportion to give us those wonderful shades that we all love to collect and sort. And so at that point, I'd like to thank, there they all the people that helped me through this wonderful initial journey. And I'll take questions, if there are any, if I have time.
Russ, we'll make time unless Yanni steps in and says, Ken, I got to be out of here in 20 minutes.
Okay. Yanni.
So I have several questions here for you. Oh,
sorry, guys. I do have to be out in.
Go ahead, Yanni.
No. I've got time.
Oh, okay. Good.
I'm trying to calculate. The fact that I'm trying to calculate means there's time.
I'll cut every second syllable out of all the words I say.
All right. Joe Bowling has a couple of questions and comments, but before we let him go, I was just going to add, as a non-scientist, since I spent my career as an accountant, with used stamps, it seems to me that you also have factors like the paper that the stamp was on when it was used, and possibly the water that was used to soak the stamp off the paper could affect.
And the storage method, for if it was from another collector, the number of variables in used stamps is enormous, but many of our most important stamps are almost impossible to find mint.
Yep. All right, Joe, go ahead.
Okay, I'm unmuted. Intaglio printing involves a wiping process after the plate is inked. And that wiping can be more or less efficient from press to press and from day to day. In the U.S., back in the 19th century, they were using paper as a wiping product, followed by the pressman's hands. Today, the high-speed presses are using water as a wiping element, high-pressure water. All of that can leave residual ink on the surface of the printed paper so that you can get a tint to the paper from the printing process. If you compare the front and the back of the paper, there'll be different shades because there was no ink applied to the back. So
right. If you take a look at the image I have in my final slide here, I think it doesn't take a lot of convincing to see that this white
pink tint
paper area is reddish.
Yes, I saw that in your first 9 slides. There were some on pink paper.
Yeah. And so, and I've seen on some of the more recent intaglio stamps a wiping process that was not uniform. So some parts of the stamp were nicely wiped and some not so.
Yeah, so it's not just the paper. It's also an artifact of printing process.
Yes.
So very, very complicated. You're right.
Tony Thompson had a comment he wanted to answer, or he wanted to insert also. Tony, just unmute.
Hi. No, I didn't have a comment. I was going to answer one of the questions about this pinkish tinge from the plates not being properly wiped, and that it's very common in the very early use of the plates. But an incredible talk. If I was to have a question, do you think it might be possible to separate out the color of the ink from the effect that the paper has on the color of the ink?
Yes, but I think it would require knowing the thickness of the ink, and it's not just its physical thickness, but its optical thickness. And there is one thing that I didn't put in here that I want to do experiments in, and that is I have some observations that suggest that the ink making contact with the paper may affect the shade of the paper. And we've all seen this by getting paper wet with different solutions, whether it be oil or water or whatever, is that the paper reflectivity changes. It gets darker or whatever. And so just like with the wiping process, it's complicated. But I think it could be done, but I think it would have to be done mathematically.
Yep. Thank you. Gary Lowe has a question. Gary, make sure you're unmuted.
I think I'm unmuted. Can you hear me?
You are.
Oh, excellent. Button actually worked. I love it. Russ, in one of your earlier slides, you were doing a comparison of TIFF files versus JPEG.
Oh, yeah.
And of course, the percentage of JPEG compression influences the loss of color detail. And literally at a 0% compression, you're just looking at what's a true TIFF file, which is what's underlying a JPEG to begin with. So my question is, what compression were you using for that slide TIFF versus JPEG measurements?
That's the basic JPEG compression. So, and giving optimal whatever the computer suggested, which is not highest, but the one little level below. And in the mint stamps that I'm going to be testing, I'm going to do it nothing but TIFF. And so that will eliminate that possibility or that uncertainty.
Yeah, and I think that's a really good idea because especially if you're not recording what kind of JPEG compression is being used, and depending on the software you're using to drive the scanner, you can end up with a different default for what that JPEG compression is. And in fact, if you set a particular JPEG compression, get out of the software, get back in, you don't know necessarily whether the software remembers the last setting or goes back to some default that it has. So JPEG can introduce a lot of uncertainty regarding the results. I think you're quite prudent in sticking with TIFF.
And not only that, but you probably noticed that the first 9 samples, the used ones, were on a black background, and the mint ones are on a white background. That I'm going to use I'm going to actually measure, like if the white area next to, like the document mat next to the stamp. And so if there is any illumination or shadowing, illumination variability in the scanner, the LED lighting, I will have a rudimentary correction factor to be able to apply to that. And so TIFF files only, and then I'm going to have a rudimentary correction factor for any variability in the CCD illumination from the scanner. And then I'm going to do what Tony said and make sure I have all of those check boxes checked or turned off in the scanner software.
I don't know, as long as we're talking about the illumination itself, I don't know where you live, but I can tell you that in some parts of the country, there is a significant enough voltage difference that the illumination can vary the same scanner over brief periods of time if you've got enough electrical.
Yes, and I was thinking of that. If you take a look at my my uncertainty measurements using the document mat, there is about twice as much variability in the y-axis, which is the axis in which the scanner travels, than in the x-axis. And so there's going to be a voltage difference causing the brightness difference. It will occur in the y-axis. And sure enough, there it is, twice as much as the x-axis. And so this is one of the reasons why I am going to measure the whiteness, if I can use that word, of the document mat next to the place I'm going to make the measurement of the brightness of the ink and the paper. Whoops. Wasn't supposed to do that. That was top secret.
Thanks,
I'll kill you all. Good question. Any more?
No, we don't have any in the queue. So one thing I do want to do first, Russ, thank you very much. Obviously an interesting presentation, and it kept our folks engaged, which is always a good deal. Before everybody leaves at the end of the day, I want to remind you that the National Postal Museum has a speaker from the Getty Museum, Olivia Cusio, who will be providing an introduction to the color of science Thursday afternoon at 4:00 Eastern Time. And similar to our presentation, you go to the NPM site, you register there, and you will be participant or an audience member in a webinar similar to this. I wanted to get that out before everybody signed off at the end of Yanni's presentation. So next and last for today, but certainly not least, we have Yanni Hofmeyr. He is going to introduce him. I'll let him get his slide presentation shared here on the screen. Here we go. Jan was born in Beaufort West, South Africa in 1953. He's been married for 49 years and has 11 grandchildren, and we assume, although he didn't say anything, that he has children as well. He now lives in Victoria, Canada. After a 25-year break to run a business and help raise the family, he started collecting again in 2005. He built an award-winning collection based on the 1861 3 cents of the United States. He also collects essays and proofs to do with philatelic invention in the USA, and for a time built a small collection of postal history relating to skirmishes in South Africa. He has exhibited FIP level on 4 continents, always getting a gold or a large gold. Jan belongs to lots of philatelic societies. His philatelic home was the Royal of Cape Town. Now it's the Victoria Stamp Club. He's also a member of the Royal of London and the U.S. Philatelic Classic Society, where he acts as their VP for international members. He publishes mainly in the Chronicle. He currently serves as their sub-editor for the essay proof section, and he has earned a number of well-deserved awards for his philatelic research. And having judged his exhibit at least once, it is tremendous. So with that, Yanni, take it away.
Thank you, Ken. Hello, everybody. So this is the stamp. I just want to make sure that, no, I think it's going to work. This is the stamp, and this began about 6 years ago because I wanted to know what I had. I had lots of variations of this particular stamp. It's the 1861 3 cent stamp of the United States. And I had anomalous expertization. And that means I had the same stamp classified as different shades. And as anybody who knows the stamp knows, the value of this dumb stamp can vary from, say, $3. Well, actually, you can't even sell them, to $5,000 or $6,000 as a function of very small differences in the shade. And so I started just by wanting to know what I had, and spent a couple of great days with Susan Smith in Washington, making measurements with a spectrometer, because I'm convinced that we have to formalize the process, and published a paper at the last Symposium about the shades. And then this symposium came up. I went to Vincent Green and thought I'd extend the work that I'd already done. But all that's happened is that I think I've ended up asking some even more fundamental questions. We do a lot to try and understand how the background stuff causes us to see different shades. And we do see different shades, and we pay different amounts of money for what we see. But how do we establish what the shade actually is? So this is sort of the agenda that I evolved. I'm going to start by talking about what I failed to do, I aim to do and what I failed to do, revisiting the problem of this fundamental question: what shade or color is a stamp? The 1861 3 cent is a great stamp to use because it has a massive shade space. It's big. And so it provides us with a great example of all the problems. And then I want to end by saying, what must we do? But I've made it ambiguous. So I say what we must do, question mark. So I'm going to make statements, but really what I want to have is a conversation. I don't think we're going to finish that conversation today. Let's summarize what I did in 2020. It's a recess printed stamp. Intaglio is the word that people are using here. And what we look for are clean and solidly inked patches. And clean meaning no covering stuff like postmarks, solidly inked so that we can't see the paper underneath. This is really key. It's thick enough in places that we can block out the paper. And so we really can get to the color of the ink. In the course of trying to answer this question, what have I actually got in my collection, I realized that I had to conduct a couple of experiments. So I'm summarizing now what I've discovered in 2020. And the first thing was that depending on, and this is kind of really obvious, should be obvious to everybody, depending on where we sample, we're going to come out with different shades. And what I did was I used standard sampling methods. So everything I'd read about in previous papers to make at least 5 samples of clean and solidly inked patches. And then I tested the variation in the shade of a stamp and found, using the just noticeable difference, I'm here using the CIE 1976 standard for color, LAB standard for color, that my average stamp contained 4 noticeably different shades within it, even when I was zeroing in to very fine gradations, in magnifying a lot, in other words. So the stamp itself varies significantly. Now, what that means is you really have to formalize the sampling. And it's not just enough to make like 10 samples. I mean, obviously, the more samples you do, the better your mean score is going to be. But you really have to formalize the sampling. So one of the questions we might just ask is, do we need to decide exactly where we're going to sample every stamp? As I say, in my case, the J and D within each stamp that I was sampling covered was 10.1, which means there are 4 noticeably different shades within each stamp. So then I thought, well, what I've really got to do is zero in, and I've got to see whether the degree of magnification makes a difference. So that was the second little experiment that I did. And that just shows the kind of magnification. The great thing about a VSC 6000, which is what I was using, was that you can really get to small blobs of ink. So you can really be sure that there's nothing else playing a role. You can get rid of the translucency effects and all the rest of it. And this was an example. If you could see the original, you'd see this is quite a nice, solidly inked patch. And I went from 8 times magnification to 61 times magnification. So I was really getting in. And what I discovered was that in my particular stamp, I had to magnify 16 times or more because anything else introduced background factors and led to what are called very big standard deviations. It's one thing to get a mean score. So this is the average profile of your stamp. But you really need to have a look at how wide the standard deviations are If they're too wide, you just have to say, this is just a mess and throw the result away. And I concluded that for my stamp, recess printed, I have to have a minimum of 16 magnification when I was sampling. And then the third thing that I had to look at was what I called, let's call it the spectrographic measurement, where you can really magnify versus what a typical expert might do. Because what an expert does is they kind of look at a blended view. They kind of step back, they make their eyes go slightly unfocused, and they try to get a blended view. And so I took patches that involved a sort of a blended view versus patches that were so solidly inked that there was no background factors playing a role, and I compared them to see whether there was a difference. I found the results were consistent, although obviously the dense patches, the very dense patches, were darker. So, armed with these results, I thought I had done well enough to develop a formal standard in that study to classify, to have a basic protocol and classify my stamps. So my basic protocol was at least five patches of solid ink, clean and solid ink, magnification 16 or greater. And although you could cut out more extraneous influences the greater you magnified, it didn't seem to matter too much as long as it was 16 or more. And I then went ahead and produced what I hoped would be something like the beginnings of formal standards for 8 of the key shades of my stamp. The LAB profile for the stamp, which you can see ranges significantly from these pink shades over here to very dark brown. There are really some wonderful shades in the stamp. And off I went, kind of quite pleased with myself. Then go to the green with a simple purpose. Measure again the same stamps using the same protocol to establish the reliability of the profiles that I was presenting. I also wanted to add additional shades. In particular, there's this stamp, which is brown-red. It's expertized as brown-red. There's this stamp, which is also expertized as brown-red. You can see that it's different. I suspected it might be Indian red. Now, the difference between, which is extremely scarce, the difference between a brown red, a really good brown red is about $200. The Indian red is $4,000 plus. So this was also a matter of commercial interest to me. I failed. It was a complete failure. The results were completely inconsistent with each other. Although I was using the Greens VSC 6000, I thought that I did everything the same way. I didn't. There were 3 differences in the method, and I really don't know whether these affected my results. In fact, in the end, the results were so variable, even though I was measuring the same stamps in what I thought was the same way, that I'm going to park this and put a big question mark next to it. And firstly, at the Smithsonian, I had to use a marble chip to pin the stamp because in the VSC it's very hot and the stamp warps. So I used a marble chip to pin it. The green uses a thin crystal slide, which really shouldn't affect the measurement. But I'm wondering whether the difference made a difference in measurement. Secondly, at Smithsonian, I took care to close the front of the machine. At the green, I was told, may not be true, that they leave the front open. I left the front open because it was quicker. And then thirdly, I was wondering whether the calibration might have affected the measurement because the marble chips are not identical. I don't know. I'm not enough of a scientist to know. But in any case, these were the only 3 ways in which my approach differed. And I got results, as I say, that were inconsistent. So I thought I need to revisit the problem. And this is something we've all touched on today in our presentations. The eye is a reflectance technology, essentially. The brain is an interpretive technology, but they function as one mechanism. You can't like switch the brain off and just let the eye do its work. And the brain needs stuff to come through from the eye. They function as one mechanism. It is exceptionally difficult to therefore conduct anything like controlled measurement using the eye and the brain. I've come to my own conclusion about what that means for our hobby. What we do is we mask. We try to cut out we try to make a comparability, or we try to drive at reliability by taking little patches, putting little, pieces of card with holes in them over the stamp to mask. Now, I want to point out that masking is nothing but magnification. So what I'm able to do with a VSC is I'm able to mask exceptionally well, because I can really zero in on a spot. So we have this problem of the reflectance technology combined with an interpretive technology which functions as one mechanism. It is great at discrimination because that's what it had to do to enable us to survive, to read, to look around in our environments and see what was going on. But without help, the eye is not good enough at magnification for what we want to do, which is classify colors, put color stamps into piles representing their color. And the brain is incapable. It is incapable of functioning without interpretation. I want to underline the word incapable. It cannot function without interpreting. So if we want to standardize color measurement, this is not a useful mechanism, even though in the end, it is the only one that matters because we collect because we love what we see. So it's the only one that we have to satisfy its needs to know what it's looking at without destroying the reason it enjoys looking at the stuff in the first place. If I can pose the problem, state the problem. And then the last thing, paradoxically, the eye-brain mechanism is so good at discriminating, it's almost too good. So it's too good at discriminating, it's not good enough at magnification, and it cannot function as an instrument for standardization. Let me delve more deeply into the problems created by discrimination. The problems created by the power of discrimination. In my original presentation, I showed the range of shades that you get with my stamp using this little thing of colored dots. It's a considerable range. And the first question I ask myself is, how many shades should there be? Discrimination causes what I call the numbers problem in the case of my stamp. I'm going to show you in a minute that there are well over 100 visible shades. No catalog will list so many shades. No collector wants to collect so many shades, which means that every shade that we then decide is worth collecting is actually a group of visibly different shades. And one of the questions we might then ask is, how many shades should there be for any stamp? Not just mine, but how many shades should there be for any stamp? And by what measure should we settle on a shade grouping that is tight enough to create something that is meaningfully coherent within itself, and covers all the variety that we see when we actually look at the stamp. So there's, first of all, the numbers problem. There's then what I called the clustering problem. Because in the case of my stamp, early collectors loved the pink shades, which are over here, and they kind of came out with just 4 shades. There's a pink, which is over here. There's a rose pink, which is over here, which is the pink that happened as the printer started to change the ink to a more stable ink. There's a pigeon blood pink, which is a particularly sort of pink. And then everything else was rose. Now, I would say that was a pathetic attempt at actually preparing a list for collectors of the shades of my stamp, because they got so obsessed with what was happening in the pink area that they completely neglected some of the wonderful shades that you get in the browner area. This is simply a human example or instance of the clustering problem. So you've not only got the how many shades should there be, by what standard when we look at any stamp across the world in philately, by what standard do we decide how many shades are needed? The second question is, how do we cluster? And anybody who's a statistician or mathematician will know that different clustering algorithms produce different answers. So that's the second problem that we have. The third problem that we have is the problem of the edge cases. Now, in expertizing, we use reference copies. Not good enough. Not good enough. Because there will always be edge cases. And in my original thing, I illustrated, you could have expert A, who has a brick red over here, and a brownish carmine stamp, and a couple of them actually. You can have expert B, who has a brick red and a brownish carmine. There's a visible kind of edge between them, but the edge is different as a function of the reference copies. So the third problem is the reference copy problem. And how do we overcome the reference copy problem, given that every shade actually involves a group of visibly different stamps? I'm emphasizing all these words because they matter. Visibly different, but we've decided they're all going to be in the pink shade or whatever. So these are the problems that are created by the power of human discrimination. Now, having failed in my original purpose, which was to, complete the formalization of the description of the colors of my stamp, and I did want to go further. I wanted to start to introduce into American philately, classic philately, additional shades which did justice to this huge area that people just called rose or brown red, but actually had some beautiful shades inside it. So I failed in all of that. I thought, well, let me do at least one thing. Let me just quantify how big the shade space is. I've got a particularly problematic stamp with a big shade space, but the analysis of the problem applies to all our stamps. So what does the shade space look like? So I took very visibly different stamps, and using, again, CIE 1976, which gives a profile, LAB, they're 3 coordinates for any shade. And they are the usual darkness one that goes from, they go from 0 to 100 for darkness. And I think they go from like minus 100 to plus 100 for the other two. I can't remember the exact endpoints of the other two. But in any case, we've got on the vertical axis white at the top and black at the bottom. We've got on the first horizontal axis here green on the left and red on the right. And we've got on this axis here blue and yellow. And any shade can be mapped within visible shade, can be mapped against these 3 coordinates. And I took the most extreme examples I could find of my stamp and mapped the edges of the shade space. And in terms of darkness, it varies from quite light, 70, and this is, by the way, looking not at paper or anything, but looking at 61 magnification. So I'm really going into blobs of ink. I wanted to get rid of all other factors. We go from really quite light pink colors, where the register on white was 79.2, down to really dark, where it was 49.8. I go from 9.8 on the towards green. It's not on the green side. It's still on the red side of the spectrum, but 9.8 on the red side of the spectrum to 31.4 on the red side of the spectrum. And I go from 6.7 on the blue side of the spectrum, on the yellow side of the spectrum, to 21.7 on the yellow side of the spectrum. And these are some of the stamps. I just shoved them in. I think it was Tony talked about how difficult it is to show things three-dimensionally. I decided I'm useless as an artist. I'm not even going to try to show perspective. I'm just going to do this in a blunt, brutal way where every unit is identical. Create a cube. We've got pale rose up here with those coordinates. We've got a brown down here with those coordinates. We've got a very dark brown. We've got a beautiful crimson rose. There are tons of shades in between. And we've got the original pink sitting up there. So when I then take the just noticeable difference of 2.3, it's a Euclidean distance. The beauty of this particular shade space, it's Euclidean, so you don't have any non-linearity problems. When I take the just noticeable difference of 2.3 and figure out how many possible shades, visibly different shades there could be in the shade space of my stamp, it turns out to be more than 750. So we really do have a numbers problem. Now, it is entirely true that there are whole areas inside here that are blank. So you take 3,000 stamps, you're not going to fill this whole space. But we have at least something like an outer limit. What we do have is well over 100 visibly different shades. How many should we have? How do we solve the numbers problem, given how good the eye and brain are at discriminating? How should we group them? Certainly not the way the classical philatelists did, which was to focus on the shades they really loved, the pink, and to completely ignore the beautiful crimson lake shade, which is exceptionally difficult to find on the brown side. And by what algorithm? Those are the three questions. I really enjoyed the work that John Savolskis did in the earlier symposia looking at the use of scanners, because most of us can't afford VSC machines. And John suggested a standard of 5.8. So the standard difference between two shades can be 5.8 as a way to reduce the problem created by the eye's ability to discriminate. If you do that, you still get 49 shades in the shade space of my stamp. And so you still get the problem. Now, how have human experts solved this problem subjectively for 150 years? This is how they've solved it. They've identified a tiny piece of the pink area and called it pigeon blood pink. They've got lots of pinks, except you've got to preserve the value of a stamp, right? If you find too many pinks, you're in trouble because suddenly they're all over the place and they don't have value anymore. So we create a bright pink, which is like really close to pink, but it's not quite pink, except I've got stamps that have been reclassified as pink because they were mistakenly classified as bright rose. You've got rose pink, which is clearly sort of more brownish and yellowish. You've got rose, which is a ton of colors, and you've now got brown, red, and you've got stamps that just don't fit. You've absolutely got the outcome of what happens when you bring this marvelous instrument that evolution has created, called the eye and the brain, to bear on the problem of our colors. And it's hopeless. It is absolutely hopeless. So here are the, if you like, two core slides. And my question to our group and to our institute is, how are we going to formalize? Because it doesn't matter that we point out all the quirks of the eye and the brain and the ways in which it makes mistakes. What matters in the end is, what really does matter, because we want to collect it, is what we see. That is what matters. We love the shades. But how do we formalize the identification of the shades, given the numbers problem, the fact that our eye and brain are too good at discriminating, the grouping problem, which you get as soon as you've got a numbers problem, and the algorithm, and what are our algorithms going to be. And I'm going to entirely throw away the reference copy problem. Not entirely. I think we still need reference copies. We need areas. If we're going to start, in this case of my stamp, we do need to identify areas where pink is, where pigeon blood pink is, where Carmine Lake is, where Indian red is. So we do need copies, but it's not going to help us to solve the problem. That's all I've got.
Well, thanks, Yanni. That leaves us all kind of hanging, doesn't it?
Well, that's the point. I think we should be, because that's where our hobby is.
Yep. I agree. We have hands going up. I don't know how to tell who they are.
I'm going to stop sharing, everybody.
Majid, all you need to do is unmute and you may speak.
Okay, I think I am. Can you guys hear me?
Yes.
Okay, I think a more fundamental question is, Jan asked about the algorithm. I think the algorithm part is actually not so important. The most important part is a metric that distinguishes between colors in a way that eyes also distinguish the same way. So RGB, as far as I know, for instance, is not a really good encoding mechanism for colors, because equal distances between RGB metric values, or at least Euclidean metric values between RGB coordinates, doesn't necessarily show you the same amount of difference. So, and there's also another problem, which is that we might see different RGB values, for instance, when we are scanning things, and we might see different values when we are actually looking at them just with plain eyes. So I think that's an important question we need to answer. And then once that is basically resolved, what is the appropriate metric and what is the right encoding mechanism? I think the algorithm will just automatically pop out. In my particular case, that I will be talking about next week, it was very simple to just use a Gaussian mixture model. I believe if we do something similar as far as encoding and as far as finding the right metric, something like a Gaussian mixture model would work fine. Usually I think the right problem is just the encoding problem. So that's my thoughts about this.
So I agree with you. That's why I used CIE 1976 LAB as my, it's not the most modern, but it was a much better starting point than RGB, for instance.
Right.
Russ, before we get to you, I've got a question from our participants. Yanni, does aging affect how the brain interprets colors?
Yeah, it really does. And so for me, one of the, again, I really didn't want to end on conclusions. I wanted to end with fundamental questions. So for me, just as Richard showed, the many analyses help us to identify what's in the ink, but they don't answer the question of how should we classify the color? That's why my paper is, what shade is your stamp? How should we classify the color? Now, if you see something different because it's aged, I kind of put that into, it's very tricky because on the one hand, there's just the sheer thing of there's a color. But on the other hand, and if we then formalized how we were going to measure color so that eye and brain played no role in it, we would get from a reflectance technology what there actually is. What are the coordinates? What are the 1976 coordinates or whatever it might be? But the fact that it's aged, so we would be able to say, well, this is what it looks like when it's aged, and it was probably pink 100 years ago. The fact that it was probably, you can't recover what it was. All you've got is what you've got. And then I think the best you can do is say, this is an old stamp. These are the current coordinates. This is kind of what we see when we look at it. It might have been pink, but I don't know. And that's as far as you can go. It's, you know, you can then decide whether it's a damaged stamp or not. I don't think you can answer that. You know, I don't know how to answer the question, frankly.
I'm reminded of the comment that Gordon Eubanks made when we had a symposium in Chicago, that when he put his color wheel of the 1847 Franklin up, he said, one thing we know is there is nobody alive today who knows what this looked like when it came across the counter in the post office.
Yeah, that's dead right.
Yep. Russ, you want to make a comment?
Yes, Yanni. It's kind of based on the previous question. Did you say that the pink grouping was the most heavily cataloged color for the original, like we're talking 100 years ago? Is that, and so there wasn't a lot of philatelists 100 years ago that were interested in the brown, and so it did not appear in the catalogs as much?
Yes, that's kind of the way in which the cataloging of the stamp evolved, because what happened was the ink was the pink was a very unstable color. And so very, very soon afterwards, it's a beautiful color. It's absolutely gorgeous. If you can find anything that comes out of an archive that hasn't been exposed to light, it's a beautiful color. But very quickly, the Post Office Department and the NBNC, who were the National Banknote Company, concluded that they had to move towards a more stable color. I don't know what inks they introduced or, what chemical compounds they introduced, but it moved towards a rose color, which is kind of a brown pink, if you like. Now, that meant that the pink was the first known rarity. And so that's where the analysis fell, was sort of pink versus the rest. And then you got rose pink, which was an intermediate color between the pink and the rose. And then at some point, there's a pink that has a sort of a lavender hue to it that is also a gorgeous color, was added. And that's extremely difficult to find, or was. That's pigeon blood pink. But
my question is
yeah,
have there been tests, and I think Ken was now alluding to this in answering the previous question.
Yeah.
Have there been tests on whether or not some of these pinks, which you said are unstable, actually have transitioned over to the brown by aging, or I think some people refer to it as sulfurizing?
Yeah.
And so it just like Ken was saying, that, 120, 150 years ago, a lot of these colors didn't exist.
Yeah, no, actually, the effect of sulfurization is quite well known in the case of this stamp, and a pink that has aged in that way is relatively easy to spot. But the color spectrum that I showed you absolutely did exist. And if anything, the darker brown shades are likely to have changed less over time. Over the course of 7 years, my hypothesis is National Banknote Company were under so much financial pressure because the contract really wasn't paying them, that they became extremely sloppy when it came to the ink mixes. Mm-hmm. And so what I showed you in terms of spectrum there has nothing to do with age. It has to do with the fact that there really were significant variations in the colors of the ink that they used.
Okay, thank you.
All right. I have no more questions in the queue. I would remind everybody that we're going to reconvene a week from today, also at 10 o'clock Eastern, for 5 more presentations. And again, the National Postal Museum has a symposium or a presentation on Thursday evening, 4:00 Eastern. And the way that you sign up for that is to go to their website and register for their webinar. I thank everybody for participating. I especially thank our authors and scientists for all the work they've done behind what went into today's presentations and next week's as well. And look forward to seeing everybody in 7 days.